Something vast is moving in the darkness, unseen, untouchable, but powerful enough to shape entire galaxies. Scientists call it dark matter, but recent discoveries suggest it's not just sitting still. It's rotating. Slowly. Silently. And if these dark halos are truly spinning, they may be the key to unlocking a hidden force that's been governing the universe from the shadows all along. If that idea doesn't stir your curiosity, you might want to check your pulse. Because today, we're plunging into one of the most radical and mind-bending frontiers in astrophysics, rotating dark matter halos. But before we continue, subscribe to the channel so you don't miss out on any of these videos. These aren't just theoretical leftovers scribbled in the margins of cosmology textbooks. They represent a potential revolution in how we understand the formation, structure, and motion of galaxies, an invisible skeleton of the universe that might not be as static as once assumed. And if these halos are indeed rotating, their implications ripple far beyond academic curiosity. They touch on the fundamental nature of matter, time, gravity, and even the birth and fate of the universe itself. But to fully appreciate the magnitude of this phenomenon, we need to unpack everything. From the most basic principles of dark matter to the complex mathematics of angular momentum in cosmic structures, and all the way to groundbreaking simulations and astronomical observations that hint at something extraordinary hidden in plain sight. Let's start at the very beginning. The term dark matter refers to a form of matter that does not emit, absorb, or reflect light, meaning we can't see it directly. Yet, its presence is unmistakable. We infer its existence through its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. When astronomers observed galaxies, they noticed something peculiar. The stars on the outer edges of these galaxies were moving much faster than they should be, given the amount of visible matter present. According to Newtonian mechanics, those stars should be flung into the void by centrifugal force, yet they remain in place. The only logical explanation? There must be a vast amount of unseen mass, dark matter, providing the extra gravity to keep those stars tethered. For decades, the prevailing model envisioned dark matter as cold, collisionless, and stationary on galactic scales, a kind of invisible, static scaffold upon which galaxies form and evolve. But in recent years, this view has started to shift. Simulations, theoretical models, and even some observational data suggest that dark matter may not be entirely passive. It might have angular momentum. It might rotate. And if it does, the implications are staggering. Rotating dark matter halos would change the entire paradigm of galaxy formation. Rotation introduces dynamics. It means that these halos are not mere background structures but active participants in shaping galactic behavior. Think about how a rotating disk of visible matter, like the spiral arms of the Milky Way, emerges from angular momentum and gravitational collapse. Now, imagine if the invisible dark matter halo enveloping that galaxy also spins. What kind of resonance or interference would that create? Could it enhance spiral arm formation? Could it influence star birth rates? Could it even impact the movement of satellite galaxies? To understand how such rotation could even occur, we need to dive into the origins of angular momentum in the early universe. Following the Big Bang, matter began to clump under gravity, forming the seeds of future galaxies. During these gravitational interactions, small tidal torques between collapsing protogalactic clouds could impart spin. This angular momentum, in theory, would be shared between baryonic matter, the normal matter we're familiar with, and dark matter. If baryons ended up rotating, why wouldn't dark matter do the same? Yet, traditional simulations often treat dark matter as a pressureless, non-interacting fluid. In this picture, it's difficult to model rotation because there's nothing for the particles to push against, no viscosity, no collisions, no magnetic fields. But newer simulations challenge that view. High-resolution N-body simulations now reveal that under certain conditions, dark matter halos can indeed exhibit coherent rotational motion. This rotation isn't always uniform. It can be clumpy, anisotropic, or even counter-rotating in regions. Still, it's enough to open a door we never knew was locked. Let's talk about angular momentum transfer. As galaxies form, baryonic matter sinks into the gravitational well of dark matter halos. As it cools and collapses, it can transfer angular momentum to the dark matter via dynamical friction. Picture a spinning figure skater pulling in their arms to spin faster. In a galactic context, collapsing baryonic clouds drag on the dark matter particles, potentially imparting a spin to the entire halo. If that spin becomes substantial, it changes how the galaxy evolves. A rotating dark matter halo can flatten, form structures, and even create torques that affect star formation and galactic mergers. There's more. Some models suggest that rotating halos might align with the spin of the central galaxy. Others propose misalignment, causing warped galactic disks or even polar rings. These predictions are testable. Astronomers can compare the orientation of dark matter halos, inferred through weak gravitational lensing, with the visible spin axes of galaxies. Early results show intriguing alignments in some cases, and stark discrepancies in others, potential signatures of rotating halos with complex dynamics. We also must consider what this rotation tells us about dark matter's fundamental properties. If dark matter halos can rotate, does that mean dark matter has some intrinsic interaction, self-interaction perhaps, that facilitates this behavior? The idea of self-interacting dark matter, SIDM, has been gaining traction. In contrast to cold dark matter, CDM, SIDM proposes that dark matter particles occasionally bounce off one another. This small amount of interaction could allow angular momentum to be shared across regions of the halo, creating coherent rotational structures. SIDM might also resolve some long-standing problems in galactic modeling, such as the core cusp problem or the too big to fail issue in dwarf galaxies. Then there's the thermodynamic perspective. In the standard model, dark matter is treated as nearly zero temperature, but rotation introduces energy, entropy, and anisotropy. A rotating dark matter halo might exhibit pressure differentials, heat flow, in a statistical sense, and perhaps even wave-like behaviors. Could there be dark matter turbulence? Vortices? This isn't just science fiction. Physicists have begun modeling such possibilities using fluid dynamics analogies. We can also explore the observational angle. While we can't see dark matter directly, we can observe its effects on light through gravitational lensing. Rotating halos might produce subtle asymmetries in lensing patterns, signatures that careful analysis could extract. Similarly, if a rotating halo interacts with baryonic matter, it might induce warps in the galactic disk or change the distribution of neutral hydrogen in the outer reaches. Observations from radio telescopes like ALMA or the Square Kilometre Array could pick up on these faint signals. And the story doesn't stop with galaxies. Rotating dark matter halos could influence entire clusters of galaxies. They could create preferential alignments, filamentary structures, or voids in the cosmic web. The large-scale structure of the universe might carry an imprint of this hidden spin, like fossil rotation etched into the scaffolding of space-time. But perhaps the most profound question is this: if dark matter halos rotate, could they affect gravity itself on cosmic scales? Modified gravity theories like MOND or emergent gravity seek to explain galactic dynamics without invoking dark matter. But what if part of the discrepancy arises not from gravity being wrong, but from our underestimation of dark matter's dynamical behavior? Rotation introduces forces, centrifugal, Coriolis, that might mimic some of the effects attributed to modified gravity. In this way, rotating dark matter halos offer a bridge between competing theories, potentially reconciling parts of both. We can even stretch further. Some speculative models suggest that dark matter might consist of exotic particles like axions, which can form Bose-Einstein condensates at galactic scales. These condensates could exhibit macroscopic quantum behaviors, including rotation. Imagine an entire galaxy wrapped in a quantum vortex, a rotating wave function of ghostly particles dictating the fate of stars and planets. It sounds absurd, yet the math checks out in certain scenarios. These are not mainstream models, but they are tantalizing glimpses into what might be. And that's only scratching the surface. When astronomers observed galaxies, they noticed a puzzling phenomenon. Stars located on the outer edges of spiral galaxies were moving at astonishingly high speeds, far faster than expected based on the gravitational pull exerted by the visible matter within those galaxies. According to the laws of Newtonian physics, these stars should have drifted away into the cosmic abyss, unable to stay bound to their galaxies. But they didn't. They remained in stable orbits, as if some unseen force was anchoring them. This invisible force, exerting a gravitational grip without emitting any light or detectable radiation, became the foundation for the dark matter hypothesis. For decades, scientists operated under the assumption that dark matter formed spherical, static halos around galaxies, acting like scaffolding that supported and stabilized the visible structures within. These halos, vast and encompassing, were thought to be non-rotating, merely passively exerting influence through gravity. However, recent research and advanced cosmological simulations have begun to challenge this assumption. What if these dark matter halos aren't static at all? What if they rotate, subtly, slowly, but with profound consequences? A rotating dark matter halo wouldn't just change our understanding of galactic dynamics, it would rewrite the fundamental framework of astrophysics. The concept of a rotating dark matter halo suggests that the dark matter surrounding galaxies may possess angular momentum, much like the visible matter within. This notion introduces an entirely new layer of complexity. Angular momentum, a fundamental quantity in physics that describes the rotation of an object, could influence how galaxies form, evolve, and interact with one another over cosmic time scales. In traditional models, dark matter particles are considered cold and collisionless, meaning they don't interact with one another through any force other than gravity. These particles, according to the standard lambda cold dark matter model, settle into large, spherical distributions around galaxies. But if these particles have net rotational motion, if they collectively swirl in a coherent direction, it implies that their formation involved torque, asymmetry, and interaction with large-scale cosmic flows. The origin of such rotation in dark matter halos could lie in the very earliest moments of structure formation in the universe. As matter began to collapse under gravity shortly after the Big Bang, quantum fluctuations and tidal forces from nearby structures could have imparted angular momentum. Over billions of years, this angular momentum may have been conserved, leading to the slow but steady rotation of dark matter halos. To understand this better, imagine the large-scale structure of the universe as a cosmic web, filaments of dark matter and gas stretching across vast distances. Galaxies form at the intersections of these filaments, in regions where matter accumulates. As matter flows along the filaments into these nodes, it can create torques, twisting the forming halos and setting them into rotation. This process, called tidal torque theory, provides one possible explanation for how dark matter halos might acquire angular momentum. But how do we detect this rotation? After all, dark matter is invisible. We can't observe it directly. However, its gravitational influence on visible matter offers a window into its behavior. Scientists have used computer simulations, some of the most advanced and computationally intensive ever developed, to model galaxy formation and evolution within a dark matter framework. These simulations incorporate the laws of physics, including gravity, thermodynamics, and hydrodynamics, to create virtual universes that closely mirror our own. In several of these simulations, rotating dark matter halos emerged naturally. The rotational velocity of these halos was not random but showed patterns, correlated with the rotational axes of the galaxies they envelop. In some cases, the alignment was striking, with the visible disk of the galaxy spinning in the same direction as the underlying dark halo. This correlation hints at a deeper relationship between visible and dark matter. If both components are rotating in concert, it suggests that their formation histories are intertwined. Galaxies and their dark matter halos may not be separate entities merely coexisting, but rather components of a single, dynamic system shaped by the same cosmic forces. Of course, not all simulations agree. The rotational behavior of dark matter halos appears to depend on several variables: the mass of the galaxy, its environment, its formation history, and the resolution of the simulation itself. High-mass halos seem to exhibit more coherent rotation, while low-mass ones are more chaotic. In dense environments, such as galaxy clusters, interactions and mergers can disrupt or enhance halo rotation. These findings raise new questions about the role of dark matter in galactic morphology. Could rotating halos explain the prevalence of spiral structures in galaxies? Could they account for anomalies in galactic rotation curves, those puzzling graphs that plot stellar velocities against distance from the galactic center? Might they even influence the orientation and alignment of galaxies within clusters and superclusters? Moreover, if dark matter halos rotate, they could generate frame-dragging effects, tiny warps in spacetime predicted by general relativity when massive objects spin. While these effects would be incredibly subtle on galactic scales, they might leave imprints in gravitational lensing patterns or cosmic microwave background anisotropies. Detecting such signatures would be extraordinarily difficult, but not impossible. Future missions and instruments, like the Vera C. Rubin Observatory, the Euclid satellite, and next-generation gravitational wave detectors, might provide the necessary sensitivity. Rotating halos could also affect dark matter detection experiments on Earth. Many direct detection efforts rely on assumptions about the velocity distribution of dark matter particles in the local galactic neighborhood. If the halo rotates, these particles may have preferred directions and speeds, altering the expected signals. Experiments like XENO-NT, LUX Zeppelin, and Darwin might need to account for this rotation in their models, or risk misinterpreting their data. Another fascinating implication involves galaxy mergers. When two galaxies collide, their dark matter halos interact gravitationally. If these halos are rotating, the dynamics become more complex. Angular momentum conservation, tidal stripping, and dynamical friction, all critical processes in mergers, would behave differently, potentially affecting the final shape, size, and rotation of the resulting galaxy. This could also help explain the formation of massive elliptical galaxies, which often show signs of past mergers but whose dark matter distributions remain poorly understood. In simulations where dark matter halos rotate, post-merger remnants tend to show more realistic properties compared to those produced in non-rotating models. Furthermore, rotating halos might influence star formation. The motion of gas within a galactic disk depends on the gravitational potential it experiences. A rotating dark matter halo could modify this potential, changing the way gas flows, collapses, and forms stars. This might explain why some galaxies have extended star-forming regions far from their centers, or why others show lopsided or asymmetric disks. All of this underscores a central theme in modern cosmology. Dark matter isn't just a passive backdrop. It's an active, dynamic participant in the cosmic story, shaping galaxies not only through its mass but through its motion. And yet, despite the growing evidence, the idea of rotating dark matter halos remains controversial. Observational confirmation is elusive. No telescope can directly image a dark matter halo, let alone measure its rotation. We rely on indirect methods, the motions of stars and gas, gravitational lensing, the distribution of satellite galaxies, and large-scale structure surveys. One such method involves the study of satellite galaxy planes. Around the Milky Way and Andromeda, satellite galaxies appear to orbit in thin, coherent planes rather than random distributions. Some researchers suggest this could be a signature of a rotating dark matter halo, one that imparts angular momentum to its satellites and aligns them in disk-like structures. Another clue comes from polar ring galaxies, where an outer ring of gas and stars orbits perpendicular to the main galactic disk. These structures may form through accretion or mergers, but their stability and persistence hint at an underlying dark matter configuration that supports such unusual dynamics. Even more tantalizing are fast radio bursts, FRBs, and gravitational wave signals. Though their connection to dark matter is speculative, some models propose that interactions with rotating dark matter structures could affect their propagation, timing, or distribution. Future observations might uncover patterns that support or refute these ideas. We're also beginning to see efforts to model dark matter with more exotic properties. Some theories propose that dark matter is not entirely cold and collisionless, but possesses self-interactions or even fluid-like behavior. In such models, rotation becomes more natural, as self-interactions could redistribute angular momentum throughout the halo. And in the most radical theories, dark matter may consist of axions, sterile neutrinos, or other particles that form condensates or waves. These fields could oscillate, twist, and rotate in ways fundamentally different from classical particles. In such scenarios, rotating dark matter halos might not be mere spherical shells, but dynamic, structured vortices, akin to cosmic whirlpools spinning silently across the universe. These particles, being cold and collisionless, were thought to simply fall into gravitational wells, settling into spherical distributions around galaxies. But if they possess angular momentum, they may behave quite differently. Rather than remaining in static halos, they could be swirling, creating vast, invisible whirlpools of mass around galaxies. This idea leads to several critical implications, each more profound than the last. First, the very structure of galaxies may be shaped in part by this hidden spin. If a dark matter halo rotates, it could exert torques and shearing forces on the baryonic, or normal, matter within. This might influence the orientation of galactic disks, the stability of spiral arms, and even the alignment of satellite galaxies. In essence, the invisible framework wouldn't just hold galaxies together, it would guide and sculpt them as they grow and evolve. Second, the idea of rotating halos could help explain anomalies that have long troubled astronomers. For instance, there are subtle mismatches between predicted and observed rotation curves in certain galaxies, discrepancies that a static halo model struggles to account for. But if the dark matter halo itself is rotating, then the distribution of gravitational forces changes. Stars could be responding not just to the central mass of the galaxy but to a swirling, dynamic sea of dark matter that wraps around them. Moreover, this rotation could leave an imprint on the cosmic microwave background, the faint afterglow of the Big Bang. If dark matter halos began to spin early in the universe's history, their rotational dynamics might subtly affect the way light from the early universe is bent and scattered. Studying these distortions could, in theory, offer indirect evidence of halo rotation, giving cosmologists a new window into the behavior of dark matter across cosmic epochs. But detecting this rotation is no easy task. Dark matter, by definition, does not emit or reflect light. It does not interact electromagnetically. That makes direct observation impossible with traditional telescopes. Instead, researchers have turned to simulations, immense, data-rich models that simulate the evolution of galaxies over billions of years, incorporating known physics and a variety of dark matter scenarios. These simulations, such as Illustris, Eagle, and Millennium, have yielded intriguing results. In some models, rotating dark matter halos emerge naturally when certain conditions are applied, such as specific distributions of initial angular momentum in the early universe. These simulations reveal that rotation is more likely in galaxies with massive disks and prominent bulges, structures that themselves exhibit high levels of angular momentum. This suggests a possible transfer of angular momentum from baryonic to dark matter components over time, a process that is still not fully understood but could involve complex gravitational interactions, mergers, and tidal forces. Another source of insight comes from gravitational lensing. When a massive object, like a galaxy or cluster, sits between a distant light source and an observer, it can bend and distort the light from that source in a phenomenon known as gravitational lensing. If a dark matter halo is rotating, it might produce asymmetrical lensing patterns, subtle distortions that deviate from what we'd expect from a static mass distribution. Although the effect is minuscule and difficult to isolate, advancements in precision measurement are beginning to make such analysis possible. Still, much of this field remains theoretical, with many competing models and interpretations. Some physicists argue that rotating halos contradict the standard cold dark matter paradigm. Others contend that rotation could emerge under modified gravity theories or alternative dark matter models, such as self-interacting dark matter, SIDM, or fuzzy dark matter composed of ultralight particles with wave-like properties. Self-interacting dark matter is particularly interesting in this context. Unlike cold dark matter, which barely interacts with itself or anything else, SIDM particles can scatter off each other, allowing energy and momentum to be redistributed within the halo. This could lead to internal dynamics that give rise to coherent rotation. The resulting halos might be less cuspy, meaning their density would peak less sharply at the center, and more core-like, aligning better with observational data for certain galaxies. Fuzzy dark matter, on the other hand, behaves more like a quantum field than a collection of individual particles. Its wave-like nature could lead to interference patterns and vortex-like structures on galactic scales. These vortexes could, in a sense, represent another form of rotational motion, not classical rotation as we know it, but quantum rotational analogs spread across light-years of space. The implications don't stop there. If dark matter halos rotate, then their angular momentum could influence the alignment of galaxies within the cosmic web. Observations suggest that galaxies are not randomly oriented but tend to align along filaments of dark matter that thread through the universe. Rotating halos might provide a mechanism for this large-scale coherence, transmitting spin from one structure to another via gravitational interactions. This raises the possibility that angular momentum in the universe is not just a property of individual objects, but a fundamental, organizing principle at all scales. From subatomic particles to superclusters of galaxies, rotation might be a universal feature, a hidden thread weaving through the cosmos. Such a realization would force us to revisit our assumptions about the origin of cosmic structure, the behavior of fundamental forces, and even the initial conditions of the Big Bang itself. Some researchers have taken this further, suggesting that if dark matter halos can rotate, then they may possess a kind of memory, retaining information about the processes and interactions that led to their formation. By studying the rotational properties of halos, we might be able to reconstruct the merger histories of galaxies, trace the influence of ancient cosmic collisions, and even map the flow of dark matter across the universe. And yet, despite all this tantalizing evidence and theoretical exploration, we are still in the early stages of understanding rotating dark matter halos. Observational proof remains elusive, simulations are limited by computational power and assumptions, and the physics of dark matter itself is still a black box. But with each passing year, the evidence grows, the models sharpen, and the questions deepen. Why would dark matter rotate? How did it gain angular momentum? What does this rotation tell us about the dark sector, a hidden realm that might contain entirely new particles, forces, or dimensions? Could rotating dark matter halos harbor exotic phenomena, like dark magnetic fields, dark turbulence, or even forms of dark energy bound within them? In trying to answer these questions, scientists are pushing the boundaries of cosmology, astrophysics, and particle physics. They are proposing missions to map dark matter distribution with unprecedented resolution, developing quantum sensors to detect ultralight particles, and exploring analogs in laboratory systems, from superfluid helium to Bose-Einstein condensates, that might mimic the behavior of rotating dark matter on small scales. The journey into the heart of rotating dark matter halos is more than a scientific quest. It is a profound reminder of how much remains unknown in a universe we thought we understood. As we peer deeper into the void, what we find is not emptiness but motion, a silent, invisible spin shaping everything we see. But detecting this rotation isn't easy. In fact, it's one of the most challenging pursuits in modern astrophysics. Since dark matter doesn't emit light or interact with electromagnetic radiation, its motion can't be observed directly through conventional telescopic methods. Instead, researchers rely on gravitational effects, how the mass of a galaxy and its surroundings distort the paths of stars, gas, and even light itself. One promising technique is gravitational lensing. When light from a distant galaxy or quasar passes near a massive object like a galaxy cluster, the mass of that object bends the light, distorting the image we see. This effect, predicted by Einstein's general theory of relativity, can be used as a kind of cosmic magnifying glass. If dark matter halos are rotating, their gravitational fields would have distinct, asymmetric signatures, subtle shifts in how light is bent depending on the direction of the rotation. These deviations are difficult to detect, but with large datasets from observatories like the Hubble Space Telescope and newer tools like the James Webb Space Telescope, astronomers are now combing through light curves and lensing patterns for any signs of swirling halos. Another potential clue lies in the motion of satellite galaxies. Larger galaxies like the Milky Way often have smaller companions, dwarf galaxies that orbit them like moons around a planet. If the dark matter halo of the host galaxy is rotating, it could influence the orbits of these satellites, causing them to line up along certain planes or exhibit synchronized motion. Interestingly, observations of the Milky Way and Andromeda have shown peculiar planar alignments of their satellite galaxies, patterns that some researchers believe could be explained by rotating dark matter halos rather than random gravitational clustering. There's also the approach of high-resolution galactic simulations. By building computational models that include not just dark matter particles, but also their potential angular momentum and interactions over billions of years, researchers have begun to produce synthetic galaxies whose behavior more closely matches what we observe in the real universe. These simulations reveal that under certain conditions, dark matter halos naturally acquire a spin, especially during mergers or through tidal torques exerted by neighboring structures. As galaxies form and collide, the gravitational dynamics impart angular momentum to the dark matter clouds enveloping them. Over time, this angular momentum builds up, causing the entire halo to slowly rotate. What's especially fascinating is how this rotational behavior might evolve over cosmic time. In the early universe, matter was more homogeneously distributed. But as it began to clump and coalesce under gravity, these irregularities grew into larger structures, filaments, sheets, and nodes in the vast cosmic web. At the intersections of these filaments, protogalaxies formed. As they accreted more mass from their surroundings, the uneven inflow of matter may have caused their dark halos to begin spinning. This would mean that rotating dark matter halos are not a late-stage feature of galactic evolution, but an ancient, primordial process dating back to the earliest epochs of structure formation. One implication of this idea is that the angular momentum of a dark matter halo could be a sort of fossil record, an imprint of the environmental conditions during the galaxy's birth. By measuring and modeling the spin of these halos, we might be able to peer back in time, reconstructing the turbulent environments in which galaxies first emerged. There's even speculation that rotating halos could influence the behavior of supermassive black holes at galactic centers. If the surrounding dark matter is rotating, it might transfer angular momentum to the accretion disk feeding the black hole, potentially affecting its spin rate, energy output, and growth over time. This connection between invisible matter and the most extreme gravitational entities in the universe is a profound one, hinting at a deep, hidden relationship that operates beneath the surface of visible phenomena. But to grasp the full implications of rotating dark matter halos, we have to zoom out even further, beyond individual galaxies, to the large-scale structure of the universe. Cosmic filaments, those vast thread-like formations of galaxies and gas, stretch for millions of light-years and are thought to be shaped by underlying dark matter scaffolding. If this dark matter is rotating, it could affect how galaxies align along filaments, how clusters form at the intersections, and how angular momentum is distributed across cosmic scales. This would mean that the universe itself has a rotational substructure, a grand, spiraling dance of invisible matter that spans the entire observable cosmos. And yet, perhaps the most provocative question remains: if dark matter halos rotate, what mechanism gave them this spin in the first place? In standard cosmological theory, angular momentum arises from tidal torque theory. As matter clumps together in a lumpy early universe, gravitational interactions between nearby protostructures twist and stretch space, creating rotational motion. But some theorists suggest that this may not be enough. They speculate that unknown physics, perhaps related to the nature of dark matter itself, could be responsible for these rotations. What if dark matter is not a single kind of particle, but a family of exotic entities with unexpected properties? Some models propose that dark matter particles could possess tiny magnetic moments or interact through unknown forces, allowing them to exchange momentum in subtle ways. Others hypothesize that dark matter may be composed of ultralight scalar fields, behaving less like particles and more like waves. In these models, wave interference could create patterns of rotation spontaneously, without the need for classical torques. Still more radical theories propose that what we're seeing isn't dark matter at all, but a sign that our understanding of gravity itself is incomplete. Modified gravity theories like modified Newtonian dynamics, and Tevis tensor, vector, scalar gravity, attempt to explain galactic rotation curves without invoking dark matter. If these theories could also account for rotational effects observed in galactic halos, they might offer an entirely different explanation for what's really happening in the cosmic shadows. But so far, the evidence continues to mount in favor of dark matter's existence, and possibly its motion. As data pours in from ever more sensitive instruments, radio telescopes mapping hydrogen gas, infrared observatories probing deep time, and gravitational wave detectors listening to the echoes of ancient mergers, we are approaching an era where the secrets of dark matter halos may finally be revealed. The next step in unveiling the mysteries of rotating dark matter halos is in the hands of next-generation observatories. Instruments like the Vera C. Rubin Observatory, which will provide unprecedented detail on the universe's large-scale structure, hold the potential to offer direct observations of the effects of dark matter rotation. This could be the breakthrough needed to connect the theory of rotating halos to observable phenomena, providing us with the definitive evidence required to cement dark matter's role in galactic dynamics. One major challenge, however, is the sheer scale and complexity of the data involved. The Rubin Observatory's Legacy Survey of Space and Time, LSST, will generate more data in a few months than humanity has collected in all of history. Sorting through such vast quantities of information is an immense task. Yet, advancements in machine learning and artificial intelligence offer a glimmer of hope. These technologies could assist in detecting patterns in data too complex or subtle for human analysis, helping researchers identify dark matter's gravitational imprint across millions of galaxies. In parallel, upcoming missions like the European Space Agency's Euclid spacecraft and NASA's Nancy Grace Roman Space Telescope are designed to study the geometry of the universe and refine our understanding of dark energy. While their primary focus is on the expansion of the universe, these telescopes will also provide vital clues about dark matter. They will map cosmic structures with unprecedented precision, potentially revealing how dark matter halos interact with visible matter in a galaxy's environment. Simulations of galactic formation are also progressing rapidly. These simulations use the laws of physics as we understand them, including general relativity and particle physics, to model how galaxies form, evolve, and interact with dark matter. With increasing computational power, astrophysicists can create highly detailed models that simulate the evolution of rotating dark matter halos across billions of years. These simulations help us predict the observable effects of rotation, providing insights into the dark matter's behavior, even when direct observation is not possible. A particularly intriguing feature of these simulations is the emergence of cosmic vortices, or spiral structures in dark matter halos. These spirals are often seen in computer models of galactic clusters, where multiple galaxies are in close proximity. The interaction of dark matter halos in these environments can induce a swirling motion, which can leave observable signatures in the way galaxies move and align within their clusters. These structures could help explain some of the mysterious behaviors observed in the outskirts of galaxy clusters, where dark matter is thought to dominate. On the theoretical side, the concept of dark matter drag has gained attention. According to this hypothesis, the rotating dark matter halos around galaxies may not be entirely stable or uniform. Instead, as these halos rotate, they could interact with the ordinary matter inside galaxies, creating friction-like effects. This drag could potentially explain the observed discrepancies in galaxy rotation curves and other phenomena that traditional dark matter models struggle to account for. If such drag effects exist, they could offer new insights into the interplay between dark matter and the visible matter we observe. The idea of dark matter drag is connected to another fascinating possibility: the role of dark matter in galaxy formation itself. If dark matter halos rotate and exert forces on the galaxies within them, this might influence the process of star formation. The interaction between the spinning dark matter and the gas clouds in a galaxy could cause them to compress, potentially triggering the birth of stars or regulating the rate at which new stars are formed. The presence of rotation in dark matter halos may thus have a profound effect on the overall dynamics of a galaxy, impacting not just its shape and size, but also its internal processes like star formation, supernova explosions, and black hole growth. This idea is supported by recent findings from simulations that show how dark matter halos influence the environment of the gas within galaxies. The spin of dark matter could induce shear forces in the gas, creating turbulence and driving the formation of dense structures that eventually collapse to form new stars. These processes are critical to understanding the life cycle of galaxies and the conditions that give rise to complex, star-filled systems like the Milky Way. Moreover, the connection between rotating dark matter halos and galaxy formation extends to the question of galaxy mergers. When galaxies collide, their dark matter halos can interact in surprising ways. The rotation of these halos may influence how the galaxies merge, potentially leading to the formation of larger elliptical galaxies from smaller spiral systems. The dynamics of such mergers, shaped by the rotation of dark matter, could have lasting effects on the resulting galaxy structure, its star formation history, and its overall evolution. In addition, the behavior of dark matter during galaxy mergers could offer crucial clues about its fundamental properties. If dark matter halos are rotating and interacting in complex ways, this could provide insights into the nature of dark matter particles themselves. Some theories propose that dark matter is made up of axions, ultralight particles that might produce distinct rotational patterns in dark matter halos. If axions are indeed responsible for the rotation, detecting their effects on galactic rotation could open up new avenues for understanding the properties of dark matter. Dark matter halos may also hold the key to understanding the observed discrepancy between the amount of visible matter in the universe and the gravitational effects observed in galaxies and galaxy clusters. This discrepancy has led scientists to hypothesize that the universe contains far more mass than we can see, and that dark matter is the missing piece of the puzzle. The rotation of dark matter halos could be the final link in proving that dark matter exists and plays a critical role in the formation and evolution of galaxies. The behavior of these halos, how they rotate, interact with visible matter, and influence galactic structure, could be the key to unlocking the true nature of dark matter and its role in shaping the universe as we know it. But for all the progress made in understanding the potential of rotating dark matter halos, there are still many questions left unanswered. How exactly do these halos spin? What drives the rotation? Tidal interactions, early cosmic conditions, or something else entirely? Could there be other, yet undiscovered forces at play? These questions highlight the exciting uncertainty that continues to drive scientific inquiry into the nature of dark matter. Each new discovery and every incremental breakthrough brings us one step closer to understanding the true structure of our universe. As we continue to explore the cosmos, using increasingly sophisticated tools to probe the depths of space, the role of dark matter, especially its rotational behavior, remains one of the most tantalizing and profound mysteries in astrophysics. While we may not yet have all the answers, each observation and theoretical model brings us closer to unraveling the hidden secrets of dark matter halos. The hunt for rotating dark matter halos is far from over, and with every passing year, our understanding of the universe continues to evolve. The story of dark matter, with all its twists, turns, and hidden layers, is far from finished. It is a story that will continue to unfold for generations to come, driving new discoveries and reshaping our view of the cosmos. As we continue to dig deeper into the study of rotating dark matter halos, the question arises: how can we refine our current theories to account for new observations? A crucial part of this endeavor lies in the evolving nature of theoretical physics itself. While the rotation of dark matter halos has been speculated through simulations and indirect evidence, our theoretical models must evolve in parallel with our growing understanding of the universe. There are a number of theoretical avenues that may help us explain the rotational behavior of dark matter in a way that aligns with both observed phenomena and new experimental results. One promising approach is the modification of the existing dark matter models, specifically those that rely on weakly interacting massive particles, WIMPs. Although WIMPs have long been the leading candidate for dark matter, new research into alternative particles has suggested that perhaps the rotation of dark matter halos could be better explained by other types of particles. One such candidate is the axion, an extremely light particle that has become an increasingly popular subject of study in recent years. Axions could potentially account for some of the unexplained characteristics of dark matter, including its effects on galactic rotation. The idea is that axions may possess unique properties that could produce a spinning dark matter halo with specific observational signatures. To test such ideas, scientists are turning to advanced particle detectors, such as the Axion Dark Matter Experiment, ADMX, which is specifically designed to detect axions. These detectors aim to measure the faint signals produced by axions interacting with electromagnetic fields. If axions are indeed responsible for dark matter's rotational behavior, these experiments could provide the direct evidence needed to revolutionize our understanding of both dark matter and the universe at large. But the rotation of dark matter halos isn't just a theoretical question, it has real, observable consequences for the formation and evolution of galaxies. As we explore this connection, it becomes clear that the rotation of dark matter plays a significant role in determining the properties of galaxies and the galaxies within large-scale cosmic structures like clusters. For example, the mass distribution of galaxies, their star formation rates, and even their dark matter content can all be influenced by the rotation of their dark matter halos. Recent observations using gravitational lensing, a technique that allows us to study the distribution of mass in the universe by observing the bending of light from distant objects, have provided important clues about the shape and rotation of dark matter halos. These studies have revealed that the halos around large galaxies are not only vast but also exhibit complex rotational patterns. By analyzing the gravitational lensing effects around galaxy clusters, scientists have been able to trace the rotation of dark matter halos and deduce their underlying structure. These observations have profound implications for our understanding of galaxy formation. In traditional models, the mass of a galaxy is assumed to be concentrated in the visible matter, stars, gas, and dust. However, gravitational lensing has shown that dark matter, which makes up most of a galaxy's mass, extends far beyond the visible components. The rotation of dark matter halos influences the dynamics of galaxies, affecting how stars move within their gravitational pull. It's possible that the rotation of dark matter may even play a role in regulating the rate of star formation, as the interaction between rotating dark matter and gas clouds could either stimulate or suppress star formation depending on the circumstances. Another area where rotating dark matter halos have significant implications is in the study of galaxy mergers. When two galaxies collide, the interactions between their dark matter halos can result in dramatic changes in the galaxy's structure and dynamics. The rotation of dark matter halos can significantly influence the way galaxies merge, with the angular momentum of the halos playing a key role in determining the final outcome of the collision. These interactions can give rise to new galaxy types, such as elliptical galaxies, which are thought to be the result of such mergers. The study of galaxy mergers provides a natural laboratory for exploring the effects of rotating dark matter halos. By examining how these halos behave during mergers, scientists can learn more about the properties of dark matter itself, how it interacts with visible matter, how it influences the structure of galaxies, and how it shapes the larger cosmic web of galaxy clusters. For example, simulations of galaxy mergers have shown that the distribution of dark matter in the halos can change during the collision, potentially altering the rotation pattern of the dark matter. These simulations provide valuable insight into how rotating dark matter halos influence the evolution of galaxies over cosmic timescales. One particularly intriguing aspect of rotating dark matter halos is their potential connection to the formation of supermassive black holes. Theories suggest that dark matter may be linked to the growth of these black holes, as the rotating mass of dark matter could concentrate at the center of a galaxy, providing the necessary material for black hole formation. This raises further questions about the interplay between dark matter and the visible universe, as the rotation of dark matter halos could influence the behavior of supermassive black holes in unexpected ways. Beyond galaxy mergers, the study of galaxy clusters offers another opportunity to investigate the rotation of dark matter halos. Galaxy clusters are massive structures that contain hundreds or even thousands of galaxies, along with a vast amount of dark matter. The behavior of dark matter in these clusters is complex, as the rotation of individual dark matter halos can influence the overall dynamics of the cluster. Observations of galaxy clusters through techniques like X-ray astronomy and gravitational lensing have provided new insights into the distribution and rotation of dark matter in these large-scale structures. One of the most fascinating aspects of dark matter in galaxy clusters is its role in the formation of large-scale cosmic structures. Dark matter is thought to be responsible for the creation of the cosmic web, a vast network of interconnected galaxy clusters and filaments. The rotation of dark matter halos in these structures plays a crucial role in shaping the large-scale distribution of galaxies. By studying the rotation of dark matter in these structures, scientists can learn more about the early universe and the processes that led to the formation of the cosmic web. The mysteries of rotating dark matter halos extend beyond the confines of our own galaxy. By studying the halos of galaxies in distant clusters, scientists can trace the evolution of the universe itself. Observing how dark matter halos behave over cosmic time scales can help us understand the conditions that led to the formation of galaxies, clusters, and the large-scale structure of the universe. As we continue to observe the universe with ever more advanced tools and techniques, the study of rotating dark matter halos promises to be a key area of research in the coming decades. We are still only scratching the surface of our understanding of dark matter and its rotational behavior. The theoretical and observational breakthroughs that lie ahead could reshape our understanding of the universe in ways we can scarcely imagine. Whether through new particle detectors, advanced simulations, or the latest observational instruments, the search for answers about rotating dark matter halos is one of the most exciting frontiers in modern astrophysics. With every new discovery, we move closer to understanding the true nature of dark matter and its crucial role in the formation and evolution of galaxies. The pursuit of understanding rotating dark matter halos is also closely tied to the fundamental question: what exactly is dark matter, and why does it behave the way it does? We've come to learn that dark matter, despite being invisible and detectable only through its gravitational effects, is a crucial player in the evolution of galaxies and large-scale cosmic structures. However, even after decades of research, dark matter remains one of the greatest unsolved mysteries in modern physics. Its role in galaxy dynamics, particularly in the rotation of dark matter halos, continues to spark intense debate and lead to innovative new models and hypotheses. To fully appreciate the importance of dark matter's rotation, it helps to consider the gravitational influence dark matter exerts on visible matter. In galaxies, this invisible substance forms massive, extended halos that extend far beyond the visible parts of galaxies, often far outstripping the visible stars and gas clouds in both mass and size. The rotation of these halos profoundly affects how stars within galaxies move. In the absence of dark matter, the stars at the outer edges of galaxies should, based on Newtonian mechanics, orbit more slowly as they get further from the galactic center. This is because there would be less mass to exert gravitational pull at those outer edges. However, when scientists measure the actual speeds of these stars, they find something very different. Stars at the edges of galaxies rotate at unexpectedly high speeds, which cannot be explained by the gravitational influence of visible matter alone. This discrepancy led to the proposal of dark matter, a type of matter that does not emit, absorb, or reflect light but instead interacts primarily through gravity. Dark matter helps explain why galaxies, especially spiral galaxies, maintain their rotational speed at large radii from the center. Without it, galaxies would not have enough mass to prevent their stars from flying off into space. The dark matter halos surrounding galaxies, while invisible, are far more massive than the visible matter within galaxies. These halos provide the additional gravitational pull that keeps galaxies intact, essentially holding them together as they rotate. But it's not just the mass of dark matter that is important, it's the way that mass is distributed and how it rotates. The rotation of dark matter halos affects the motion of everything within a galaxy, from stars to gas clouds to even the supermassive black holes at the center of many galaxies. The behavior of these halos is intricate and complex. In many cases, dark matter halos are believed to be in a state of equilibrium, rotating smoothly and symmetrically. However, there are instances where the distribution of dark matter within these halos may not be as uniform as once thought. New simulations and observational evidence suggest that dark matter halos may be lopsided, warped, or otherwise irregular in their rotation, affecting the dynamics of the galaxy in unexpected ways. The rotational behavior of dark matter halos could even influence the shape of the galaxy itself. Galaxies are often classified by their appearance: spirals, ellipticals, and irregular galaxies, but the rotational influence of dark matter could contribute to these classifications. One particularly interesting area of research is the study of halo shapes. Recent work has proposed that dark matter halos may not always be spherical, as was previously assumed, but instead could take on more complex shapes, such as elongated or even triaxial halos. These shapes would have a significant impact on the dynamics of galaxies, as the gravitational influence of dark matter would vary depending on the direction relative to the galaxy. The presence of these elongated or irregular halos could influence how galaxies interact with one another, particularly during galaxy mergers, as well as how galaxies evolve over time. Another important aspect of rotating dark matter halos is their role in the formation and growth of structures on much larger scales. For instance, when galaxies come together to form galaxy clusters, the dark matter halos of each galaxy merge into a single, larger dark matter halo. This process is crucial for the growth of galaxy clusters, which are the largest gravitationally bound structures in the universe. The rotation of dark matter in these clusters can influence their overall shape and structure, and it may also play a role in the formation of supermassive black holes. Supermassive black holes, which reside at the centers of most galaxies, are thought to be closely tied to the properties of their host galaxies, including the rotation of the dark matter halos. The angular momentum of the dark matter halo may be transferred to the gas and stars in the galaxy, which could, in turn, influence the growth of the black hole. Some theories even suggest that dark matter could be directly involved in the formation of supermassive black holes, either by providing the raw material for their creation or by influencing the processes that allow them to grow. Moreover, the study of rotating dark matter halos doesn't just inform us about the present structure of the universe. It also sheds light on its past. The rotation of dark matter halos could hold clues about the earliest stages of galaxy formation, helping us understand how galaxies came to be and how they evolved. One hypothesis is that dark matter played a central role in the formation of the first galaxies, providing the gravitational scaffolding around which visible matter could condense and form stars. If this hypothesis is correct, the study of rotating dark matter halos could give us a glimpse into the very beginnings of the cosmos. Interestingly, the study of dark matter and its rotation is not confined to the realm of astrophysics. The nature of dark matter also raises important questions in fundamental physics, particularly in the context of particle physics. As we search for dark matter, scientists are looking for direct evidence of its existence in laboratories on Earth. Some of the most cutting-edge experiments in physics, such as those conducted at the Large Hadron Collider, aim to detect the elusive particles that could make up dark matter. One theory that has gained traction is the idea that dark matter might be composed of weakly interacting massive particles, WIMPs. These particles, if they exist, could be detected through their interactions with normal matter, albeit very weakly. Other candidates for dark matter include axions, sterile neutrinos, and primordial black holes. Each of these candidates would have a different effect on the rotation of dark matter halos, which in turn would impact the formation of galaxies and their rotational dynamics. The quest to identify the true nature of dark matter is ongoing, and every new piece of evidence, whether from direct detection experiments or astronomical observations, brings us closer to answering one of the most profound questions in physics. Furthermore, rotating dark matter halos also have implications for cosmology and the study of the large-scale structure of the universe. The universe is filled with vast networks of galaxies connected by vast cosmic filaments of dark matter. The rotation of dark matter halos on these scales could influence the distribution of galaxies and how they are arranged into large-scale structures. One of the most important open questions in cosmology is why the universe appears to have a cosmic web structure: galaxies, clusters, and superclusters of galaxies arranged in long, interconnected filaments. The role of dark matter, and its rotation, could be a key factor in explaining this large-scale structure. The implications of rotating dark matter halos extend beyond simply understanding galaxies and their dynamics. They may also shed light on the ultimate fate of the universe. Dark matter is thought to make up about 27% of the total energy content of the universe, and its gravitational effects on the large-scale structure are significant. Understanding how dark matter behaves, particularly in the context of its rotational properties, could help us unlock mysteries about the expansion of the universe, its eventual fate, and the nature of cosmic forces such as dark energy. The fascinating complexity of rotating dark matter halos, with their gravitational effects, influence on galaxy dynamics, and connection to fundamental physics, makes them an essential area of study for scientists seeking to understand the workings of the universe. Each discovery brings us closer to uncovering the true nature of dark matter and its role in shaping galaxies, clusters, and the entire cosmos. As we look ahead, the continuing exploration of dark matter promises to yield groundbreaking insights that could forever change our understanding of the universe's past, present, and future. The exploration of rotating dark matter halos continues to have profound implications for our understanding of the universe. As more advanced telescopes and observatories are developed, our ability to peer deeper into the cosmos and study the behavior of dark matter will only improve. However, this is a journey that has only just begun. Every discovery not only contributes to our understanding of how galaxies and large-scale structures form but also leads to new questions that push the boundaries of our knowledge. One crucial aspect that requires further attention is the specific distribution and behavior of dark matter at the outskirts of galaxies. The outer regions of dark matter halos are some of the most difficult to observe due to their faintness. However, astronomers have developed innovative techniques to probe these distant regions. One of these methods involves observing the rotation curves of galaxies. By measuring the speed at which stars move in the outermost parts of galaxies, scientists can infer the distribution of mass, both visible and invisible, within a galaxy's dark matter halo. Recent advancements in gravitational lensing have also provided insights into the behavior of dark matter halos. Gravitational lensing occurs when a massive object, such as a galaxy or galaxy cluster, bends the path of light from more distant objects behind it. This phenomenon allows scientists to map out the distribution of dark matter by observing how light from background galaxies is distorted. When applied to galaxy clusters, this technique provides valuable data about the shape and size of dark matter halos and offers a glimpse into their rotational properties. Despite these advances, the full understanding of rotating dark matter halos remains elusive. One of the key challenges lies in reconciling observations with theoretical models. For many years, scientists have used simulations to model the behavior of dark matter in galaxies. These simulations, based on the assumption that dark matter is composed of particles that interact only weakly with normal matter, have proven to be quite successful in reproducing the general structure of galaxy halos. However, they often struggle to explain certain phenomena, such as the exact shape of dark matter halos or the observed differences in rotation speeds across different galaxies. In some cases, it has been suggested that the discrepancy between observations and simulations may arise from an incomplete understanding of the physics of dark matter. Some theories propose that dark matter may not be composed of traditional particles at all but could involve entirely new forms of matter that behave in ways we don't yet understand. One such possibility is the idea of self-interacting dark matter. This theory suggests that dark matter particles could interact with one another in addition to interacting gravitationally with normal matter. If this is the case, it could explain some of the observed discrepancies in galaxy rotation curves and the shape of dark matter halos. Another avenue of exploration involves the study of galaxy mergers. When two galaxies collide, their dark matter halos merge as well. The rotational dynamics of these merged halos provide a natural laboratory for studying how dark matter behaves under extreme conditions. By observing the results of galaxy mergers, astronomers can test theories of dark matter and refine their models to account for the complex interactions between galaxies and their dark matter halos. For example, the discovery of dark matter streams. In some galaxy clusters, regions where dark matter seems to flow along a specific direction, has raised intriguing questions about the nature of dark matter and how it may interact during galaxy collisions. The rotation of dark matter halos also plays a role in the broader context of cosmology, particularly when it comes to understanding the formation of the universe itself. The standard model of cosmology, known as the lambda-cold dark matter model, posits that dark matter played a critical role in the formation of the first structures in the universe. According to this model, dark matter clumped together under gravity in the early universe, creating the scaffolding around which ordinary matter could condense to form galaxies. Understanding how dark matter halos rotate could provide valuable insights into the dynamics of this process and help refine our models of cosmic evolution. In recent years, alternative theories to the lambda-cold dark matter model have emerged, challenging the idea that dark matter is solely responsible for the formation of galaxies and large-scale structures. Some of these theories propose modifications to our understanding of gravity, suggesting that the effects attributed to dark matter could instead be the result of new gravitational forces acting on visible matter. These theories, collectively known as modified gravity models, offer alternative explanations for the behavior of dark matter halos and their rotational properties. One of the most well-known modified gravity theories is modified Newtonian dynamics, MOND, which suggests that Newton's laws of gravity need to be adjusted at very large scales. According to MOND, the discrepancy between the observed rotation curves of galaxies and the predictions of Newtonian gravity could be explained by a modification to the gravitational force in low acceleration environments, such as those found in the outer regions of galaxies. While MOND has had some success in explaining galaxy rotation curves without invoking dark matter, it faces significant challenges in explaining other observations, such as the cosmic microwave background and the behavior of galaxy clusters. Despite these challenges, modified gravity theories remain an active area of research, with some scientists exploring the possibility that both dark matter and modifications to gravity could coexist in a more complex framework. By incorporating both ideas into a unified model, researchers hope to reconcile the observations that dark matter alone cannot fully explain and offer a more complete picture of the universe's fundamental workings. As our observational tools continue to improve, it is likely that we will gain new insights into the behavior of dark matter and its role in the rotation of galaxy halos. New space missions, such as the James Webb Space Telescope, promise to provide more detailed observations of distant galaxies and galaxy clusters, allowing scientists to map dark matter halos with greater precision. Meanwhile, on Earth, experiments like the search for direct dark matter detection will continue to push the boundaries of particle physics, offering the potential for breakthroughs that could finally reveal the nature of dark matter. The study of rotating dark matter halos represents a crucial frontier in our quest to understand the universe. It sits at the intersection of astrophysics, cosmology, and particle physics, and offers the potential for groundbreaking discoveries that could reshape our understanding of the cosmos. As scientists continue to probe the mysteries of dark matter, we move closer to answering some of the most fundamental questions about the nature of the universe. What is dark matter? How does it interact with ordinary matter? And what role does it play in the evolution of galaxies and the structure of the cosmos? The journey to unravel these questions is ongoing, and each step brings us closer to the truth. Whether it's through simulations, observational data, or new theoretical models, the quest to understand rotating dark matter halos is not just about answering specific questions, it is about uncovering the deep, underlying forces that shape the universe itself. In many ways, the study of dark matter is a reflection of humanity's broader desire to understand our place in the cosmos and the fundamental laws that govern it. As we continue to explore this fascinating subject, we remain on the precipice of discovery, waiting for the next breakthrough that will bring us one step closer to unlocking the secrets of the universe. The study of rotating dark matter halos remains one of the most exciting and enigmatic fields in modern astrophysics. While our understanding has advanced significantly over the years, new questions constantly arise, further deepening the mystery of this invisible component that plays such a critical role in the structure and dynamics of galaxies. As researchers continue to explore dark matter's properties, we may uncover not only the secrets of the universe's most elusive substance but also the potential to revolutionize our understanding of the very nature of reality itself. One key aspect that continues to intrigue scientists is the effect of dark matter on galaxy formation. It is clear that dark matter is crucial for the formation of galaxies. The gravitational influence of dark matter is thought to act as a cosmic scaffold, around which visible matter, including stars and gas, gathers. Without dark matter, the gravitational pull needed to form the dense clusters of stars that we observe in galaxies might not be possible, as visible matter alone would be insufficient to create the necessary gravitational wells. However, the detailed mechanics of how dark matter influences galaxy formation are still unclear. Current simulations show that dark matter halos provide a framework for galaxies to grow, but they do not fully capture the subtleties of how these halos evolve over time. What is particularly intriguing is how dark matter interacts with baryonic matter, the normal matter that makes up stars, planets, and everything we can see. This interaction is thought to be extremely weak, with dark matter primarily affecting baryons through gravity. However, some theories suggest there could be additional, unknown forces at play. The idea that dark matter might interact in more complex ways with normal matter has led to the proposal of various new physics models. One of these models, called the dark matter-baryon interaction, posits that dark matter particles could have very faint interactions with normal matter, influencing the way galaxies and structures evolve. This theory is still in its early stages and is difficult to test, as the interactions would be too weak to detect directly. Nevertheless, some scientists are optimistic that new technologies and experimental setups could eventually provide evidence for such interactions, further expanding our knowledge of dark matter. Additionally, the distribution of dark matter in galaxies is not as straightforward as once thought. Early models of dark matter halos, based on the assumption that dark matter behaves like a simple, smooth distribution of particles, predicted that the outer regions of galaxies should be spherical. However, more recent observations have shown that dark matter halos may not be perfectly spherical. Instead, they can be lopsided, with complex structures that reflect the history of galaxy mergers and other cosmic events. This means that the shape and rotation of dark matter halos are not fixed, and they can evolve over time. The role of galaxy mergers in shaping dark matter halos is another topic of intense study. When two galaxies collide, their dark matter halos also interact, often merging into a single, more massive halo. The dynamics of these mergers can provide valuable information about the nature of dark matter. In some cases, the merging process may result in a dark matter halo with a unique structure or behavior, potentially offering clues about the fundamental properties of dark matter. The discovery of dark matter cores in some galaxy clusters is one example of how these interactions might manifest. A dark matter core is a region where the density of dark matter appears to decrease significantly compared to the surrounding areas. This phenomenon is thought to occur during galaxy mergers, when the gravitational interactions between galaxies cause the dark matter to redistribute in a way that creates a core. The existence of dark matter cores challenges the traditional notion of dark matter halos as smooth, non-interacting structures, suggesting that dark matter may have more complex properties than we previously imagined. As we probe deeper into the nature of dark matter, we continue to refine our understanding of its rotational behavior. Dark matter's rotation, or lack thereof, has far-reaching implications for our cosmological models. One aspect that is still under intense scrutiny is the density profile of dark matter halos. Early theories suggested that dark matter halos followed a simple, universal density profile, often referred to as the Navarro-Frank-White (NFW) profile. However, recent observations have shown that the distribution of dark matter may vary significantly from one galaxy to another, with some halos exhibiting a much steeper or shallower density gradient than others. This variation challenges the idea that there is a single, universal, form for dark matter halos. It also suggests that the properties of dark matter halos may be influenced by a variety of factors, such as galaxy type, size, and environment. For example, smaller galaxies and those in dense environments might exhibit different dark matter distributions compared to larger, isolated galaxies. Understanding these variations is essential for developing more accurate models of galaxy formation and evolution, as well as for testing the validity of different dark matter theories. One promising area of research that may help shed light on the properties of dark matter halos is the study of dwarf galaxies. These small, faint galaxies are often considered relics of the early universe and provide a unique opportunity to study the fundamental properties of dark matter. Dwarf galaxies are thought to contain a significant amount of dark matter relative to their visible mass, making them ideal candidates for studying dark matter halos in greater detail. Recent surveys have revealed that the dark matter halos of dwarf galaxies exhibit a wide range of structures, from compact cores to more diffuse, extended halos. These observations suggest that the dark matter in dwarf galaxies may behave differently than in larger galaxies, providing valuable insights into the variety of dark matter distributions in the universe. The study of rotating dark matter halos is also intricately tied to the search for direct evidence of dark matter particles. While current observational methods allow us to infer the existence of dark matter by studying its gravitational effects on galaxies and galaxy clusters, detecting dark matter directly remains one of the greatest challenges in modern physics. Experiments like the Large Hadron Collider and underground detectors, such as those used in the search for weakly interacting massive particles, WIMPs, are ongoing efforts to detect dark matter particles directly. These experiments are highly sensitive to the faintest signals, but as of now, no definitive evidence for dark matter has been found. The detection of dark matter would mark a monumental breakthrough in our understanding of the universe. If dark matter particles are detected, they could provide key insights into the fundamental forces and particles that make up the universe. More importantly, it would help us better understand how dark matter influences the rotation of galaxy halos and its role in the larger cosmic picture. In the meantime, indirect evidence from observations of galaxy rotation curves, gravitational lensing, and other phenomena will continue to be our primary tools for studying dark matter halos. Ultimately, the study of rotating dark matter halos represents a crucial piece of the puzzle in understanding the cosmos. The interplay between dark matter and normal matter is central to our understanding of galaxies, the large-scale structure of the universe, and the very nature of gravity itself. As new observational techniques are developed, and as our theoretical models evolve, we may be on the verge of discovering new aspects of dark matter that will transform our view of the universe. The mystery of dark matter remains unsolved, but each step forward in our research brings us closer to answering one of the most profound questions in modern science: what is dark matter, and how does it shape the universe? As we continue to explore the rotating dark matter halos, it's crucial to understand that dark matter isn't just a static backdrop to galaxies. It actively participates in shaping the properties and behavior of galaxies in a way that directly affects everything from their formation to their rotation curves. These halos, the vast and often invisible frameworks of dark matter surrounding galaxies, govern how galaxies move, how they interact with each other, and even how they evolve over time. The influence of dark matter on the rotational behavior of galaxies is subtle, yet powerful, and understanding its effects can unlock the mysteries of cosmic evolution. One of the most intriguing aspects of dark matter halos is how they affect the rotational velocity of galaxies. In the 1970s, astronomer Vera Rubin and her colleagues made a groundbreaking observation that the outer stars of galaxies were rotating much faster than they should, based on the visible matter present. According to the laws of gravity and the visible mass in galaxies, the stars should have been moving slower as they orbited farther from the galactic center. Instead, the stars maintained a relatively constant speed, even at great distances from the galaxy's center. This discrepancy suggested the existence of some unseen mass, an invisible substance that provided additional gravitational pull, which was later identified as dark matter. The rotation curves of galaxies, which plot the speed of stars as a function of their distance from the center of the galaxy, have been key in revealing the presence of dark matter. The flat rotation curves, where stars at the outer edges of galaxies rotate at nearly constant speeds, cannot be explained by the visible matter alone. This led to the hypothesis that galaxies are surrounded by a massive, unseen halo of dark matter that extends far beyond the visible boundaries of the galaxy. The dark matter halo provides the necessary gravitational force to explain the observed rotational behavior. What's fascinating about dark matter halos is that their rotation is thought to follow a pattern that is distinct from the rotation of visible matter. The visible matter in galaxies, like stars and gas, is concentrated in the center and is much more affected by the forces we can directly observe, like electromagnetic radiation. In contrast, the dark matter halo surrounds the galaxy, and its influence is felt primarily through gravity. This distinction in behavior is why dark matter halos are often thought to rotate in a more uniform manner compared to the uneven rotation of the visible components of galaxies. In recent years, astronomers have been able to map out the structure of dark matter halos in much greater detail than ever before. One of the key methods for studying dark matter halos is gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity. Gravitational lensing occurs when the gravitational field of a massive object, like a galaxy or a galaxy cluster, bends and distorts the light coming from objects behind it. This bending of light allows astronomers to infer the presence and distribution of dark matter in the foreground objects, revealing the shape and size of dark matter halos. Through gravitational lensing, astronomers have discovered that dark matter halos are often not as simple and smooth as once thought. In fact, some dark matter halos exhibit a variety of shapes and features that reflect the history of galaxy mergers and other cosmic events. These observations challenge the early models of dark matter halos as perfectly spherical or uniform objects. Instead, they suggest that the dark matter halo of a galaxy may be more dynamic and complex, shaped by the interplay between dark matter and the galaxy's evolution. Another breakthrough in the study of dark matter halos came with the discovery of subhalos, smaller clumps of dark matter that exist within larger dark matter halos. Subhalos are believed to be remnants of smaller galaxies that were absorbed by a larger galaxy in a process known as accretion. The discovery of these subhalos has provided valuable insight into the way dark matter interacts with itself and with the visible matter in galaxies. These subhalos can affect the dynamics of galaxies, including their rotation curves, and may even play a role in the formation of galaxy clusters. The study of rotating dark matter halos also has profound implications for our understanding of the evolution of galaxies. In the past, galaxy formation was thought to be a relatively straightforward process, with galaxies simply accreting matter over time. However, recent research has shown that the evolution of dark matter halos is more complex, with galaxies undergoing numerous mergers and interactions throughout their lifetimes. These events can dramatically alter the structure and dynamics of dark matter halos, influencing the rotation of galaxies and their overall behavior. One of the most important aspects of dark matter halos in this context is their role in stabilizing galaxies. Without the gravitational pull of dark matter, galaxies would likely be much less stable, with stars and gas being pulled out of the galaxy's center by the forces at play. Dark matter's gravitational influence helps keep galaxies intact, allowing them to continue forming stars and evolving over time. This stabilizing effect is particularly important in the early stages of galaxy formation, when the visible matter in a galaxy is still in the process of coming together. The influence of dark matter on galaxy rotation and stability extends beyond individual galaxies. It also plays a crucial role in the larger-scale structure of the universe. Galaxy clusters, which are massive collections of galaxies bound together by gravity, are also surrounded by enormous dark matter halos. These halos provide the gravitational glue that holds galaxy clusters together, preventing them from flying apart due to their own motion. In fact, dark matter is believed to be responsible for the vast majority of the mass in galaxy clusters, with visible matter making up only a small fraction of the total mass. Understanding the role of dark matter in galaxy clusters is essential for understanding the large-scale structure of the universe. The distribution of dark matter in clusters can reveal important information about the history of the universe and the forces that shaped its evolution. It is also key to understanding the dynamics of galaxy clusters, including how galaxies within these clusters interact and evolve over time. One of the most exciting developments in the study of dark matter halos is the possibility of detecting the effects of dark matter beyond its gravitational influence. While dark matter interacts with normal matter primarily through gravity, there are theories suggesting that it may also interact through other, more subtle forces. For example, some researchers have proposed that dark matter could have a faint electromagnetic interaction, which might allow it to affect the behavior of galaxies in ways that go beyond its gravitational influence. These ideas are still speculative, but they open up new avenues for exploring the nature of dark matter and its role in the universe. If such interactions could be detected, it would mark a revolutionary breakthrough in our understanding of dark matter. It would also provide a powerful new tool for studying the rotation and behavior of dark matter halos. For now, however, researchers are focusing on the more established methods of studying dark matter, including simulations, observations of galaxy rotation curves, and gravitational lensing. Despite these challenges, the study of dark matter halos and their rotation remains one of the most exciting and promising areas of astrophysics. With each new discovery, we inch closer to understanding one of the universe's most profound mysteries. The mysteries surrounding dark matter halos continue to challenge our current models of the cosmos, but they also offer the tantalizing possibility that we are on the cusp of a new era in our understanding of the universe. As we continue to probe deeper into the subject of rotating dark matter halos, we find ourselves standing at the precipice of major breakthroughs in both theoretical and observational astrophysics. Dark matter, though invisible to the naked eye, exerts its influence through gravity in a way that fundamentally shapes the very structure of the universe. Understanding how this elusive substance interacts with galaxies, clusters, and the fabric of space-time itself is a quest that could redefine how we understand gravity, matter, and the cosmos. The idea that dark matter halos are not merely static clumps of unseen mass, but rather dynamic, evolving structures, challenges earlier paradigms of galaxy formation and evolution. Over the last few decades, scientists have begun to realize that these halos may be far more complex than previously thought. The gravitational pull of dark matter not only influences the motion of galaxies but also interacts with the cosmic web, the vast network of galaxy clusters and filaments that stretch across the universe. These interactions could help explain the large-scale structure of the universe, giving us a window into the events and processes that shaped the cosmos since its earliest days. Dark matter halos are often depicted as spherical regions of dark matter that surround galaxies, but in reality, their shape and behavior can be more varied. Some halos exhibit a more flattened, elliptical shape, while others may be irregular, reflecting the history of the galaxy they surround. These shapes can provide important clues about the galaxy's past, such as whether it underwent a merger or accretion event. For instance, galaxies that have collided with or merged with other galaxies may have dark matter halos that are disturbed or asymmetrical, showing clear signs of the violent processes that shaped them. The history of galaxy mergers is key to understanding the properties of dark matter halos. Galaxies, especially in the early universe, were constantly interacting with one another. When two galaxies collide, their dark matter halos merge, and the resulting halo may be larger, more extended, and more complex. This merger process leads to the creation of what scientists refer to as hierarchical structures, where smaller galaxies come together to form larger ones, and dark matter plays a central role in binding these structures together. One particularly fascinating aspect of these mergers is the way they can affect the dark matter distribution within a galaxy. During a collision, dark matter does not interact through electromagnetic forces, meaning it can pass right through the galaxies involved without significantly altering its own structure. However, the visible matter, gas, stars, and dust, can interact strongly, potentially creating shock waves and redistributing the gas within the galaxies. While the visible matter is altered, the dark matter halo remains relatively unaffected, maintaining its overall shape and structure. This interplay between visible and dark matter is one of the key drivers of galaxy evolution, and understanding it can help us reconstruct the history of galaxies. Moreover, the dynamics of dark matter halos also play a crucial role in how galaxies form and evolve over time. Without the presence of dark matter, galaxies would lack the gravitational foundation needed to hold together their stars, gas, and dust. In essence, dark matter acts as a cosmic scaffold, supporting the structure of galaxies. The presence of dark matter not only influences the rotation of galaxies, but it also regulates the rate at which they form new stars. Without dark matter, galaxies would have a much harder time retaining their gas and dust, which is necessary for star formation. Dark matter halos may also help regulate the flow of gas into and out of a galaxy, influencing its star formation rate. Recent studies have provided evidence that dark matter halos are not uniform in density. Instead, the density of dark matter tends to peak at the center of the galaxy, and then gradually declines as you move outwards. This distribution is key to understanding the relationship between dark matter and galaxy dynamics. The inner regions of the halo, which are denser, provide more gravitational pull, influencing the motion of stars and gas near the galaxy's core. In contrast, the outer regions of the halo, which are less dense, have less of an effect on galaxy rotation. However, the extended dark matter halo still plays a vital role in maintaining the overall gravitational stability of the galaxy. Interestingly, simulations of dark matter halos suggest that they are likely to be more concentrated in the center and more diffuse in their outer regions. These simulations also reveal that the dark matter distribution within a galaxy can vary depending on the size and mass of the galaxy. Larger galaxies tend to have more massive and extended dark matter halos, while smaller galaxies may have less dense halos. This variation in dark matter distribution is thought to be a result of the different processes that shape galaxies over time, including mergers, accretion, and the interplay between dark matter and visible matter. One area of active research in the study of dark matter halos is the search for clues about the fundamental nature of dark matter itself. While we have observed its gravitational effects on galaxies and clusters, dark matter remains a mysterious substance. Researchers are investigating whether dark matter could be composed of particles that interact in ways other than gravity. Some theories suggest that dark matter might be made up of weakly interacting massive particles, WIMPs, while others propose that it could be made of axions, particles with extremely low mass that interact only through gravity and the strong force. Still other hypotheses propose that dark matter might be composed of sterile neutrinos, exotic particles that do not interact with regular matter except through gravity. Detecting these particles directly is one of the greatest challenges in modern physics. While dark matter cannot be observed through conventional means, such as emitting light or radiation, it can be detected indirectly through its gravitational effects on visible matter. Current experiments are designed to detect the subtle effects of dark matter on ordinary particles, such as the interaction of WIMPs with atoms or the rare collision of dark matter particles with visible matter. These experiments, which include detectors buried deep underground to shield them from cosmic rays, are continuing to push the boundaries of our understanding of dark matter. Another intriguing possibility is that dark matter could be responsible for some of the more mysterious phenomena we observe in the universe, such as the behavior of galaxies and clusters or the formation of galaxy filaments. The idea that dark matter could be linked to the cosmic web, the vast, interconnected structures of galaxies and dark matter, is a topic of active research. The gravitational influence of dark matter may help shape the large-scale distribution of galaxies, leading to the formation of clusters and filaments that span vast distances across the universe. These galaxy filaments, which are part of the cosmic web, are some of the largest structures in the universe, stretching across hundreds of millions of light-years. Dark matter is believed to play a key role in their formation by providing the gravitational pull needed to draw galaxies together. The interaction between dark matter and the galaxies within these filaments could provide important clues about how the universe evolved after the Big Bang. As we continue to observe and map the cosmic web, we may uncover new insights into the distribution of dark matter and its role in shaping the structure of the universe. Understanding the behavior of dark matter in these larger structures is crucial for several reasons. First, it can help us understand how galaxies form and evolve within the larger cosmic landscape. Second, it can shed light on the dynamics of galaxy clusters and the interactions between galaxies in these clusters. And finally, it can provide valuable clues about the fundamental properties of dark matter itself, including its mass, its distribution, and its potential interactions with other forms of matter. Ultimately, the study of rotating dark matter halos and their impact on galaxies is more than just an academic exercise. It's a quest to unlock one of the greatest mysteries of the universe. The role of dark matter in the evolution of galaxies, clusters, and the large-scale structure of the cosmos is central to our understanding of how the universe works. The search for dark matter, its properties, and its interactions with visible matter will continue to drive research in astrophysics for years to come. As we continue to unravel the mysteries of dark matter and its impact on the universe, the role of rotating dark matter halos becomes increasingly significant in our understanding of cosmic structures. It's clear that these halos are not mere passive components of the universe. They actively shape the way galaxies move, form, and interact with one another. The dynamics of dark matter halos are also essential for understanding not only the large-scale behavior of galaxies but also the deeper, more fundamental questions about the nature of dark matter itself. One of the key puzzles that scientists are working to solve is the relationship between dark matter halos and the central supermassive black holes found at the centers of many galaxies. This connection is far from trivial. Supermassive black holes are thought to play a crucial role in galaxy formation and evolution, and the presence of a rotating dark matter halo could affect the way these black holes grow, evolve, and interact with their host galaxies. The influence of the dark matter halo on the dynamics of stars and gas within a galaxy could, in turn, impact the growth of the central black hole. While the exact mechanisms remain unclear, it is theorized that the dark matter halo could provide both the necessary gravitational foundation for the formation of the central black hole and also influence its growth over time. The halo's rotation and its gravitational effects may create the conditions that funnel material toward the black hole, accelerating its growth and fueling its activity. Additionally, the interactions between dark matter and regular matter within the halo could play a role in regulating the amount of gas that falls into the black hole, thus influencing the rate at which it accretes matter. The question of how dark matter interacts with visible matter within a galaxy has prompted the development of several innovative theories. One such theory is the idea of self-interacting dark matter, SIDM. In this model, dark matter particles would not only interact gravitationally but also collide with one another, exchanging energy and momentum. This type of interaction could help explain some of the observed phenomena that are difficult to reconcile with the standard cold dark matter, CDM, model, such as the distribution of dark matter in galaxy clusters. SIDM could also help explain the unique distribution of dark matter observed in certain galaxies, where the dark matter halo is more concentrated in the center and less diffuse in the outskirts. The self-interacting nature of dark matter is an exciting hypothesis because it opens up new possibilities for understanding the evolution of galaxies. If dark matter does interact in this way, it could lead to more complex halo structures and dynamics, which could provide insights into the processes that shape galaxies. This theory also raises the possibility that dark matter could be more visible than previously thought, especially if we can detect these interactions through future experiments. Current experiments are focused on detecting faint signals that could arise from such interactions, such as the scattering of dark matter particles with ordinary matter. If these experiments succeed, they could provide direct evidence for SIDM, revolutionizing our understanding of dark matter and its role in the cosmos. Another intriguing aspect of rotating dark matter halos is their potential to influence the formation of galactic rings. Rings, such as the well-known rings around Saturn, are not unique to planetary systems. In fact, galactic rings, often formed by the interaction of a galaxy's disk with its dark matter halo, can be seen in certain galaxies. These rings are thought to be the result of complex gravitational interactions between the galaxy's visible matter and the dark matter halo. Some theories suggest that the rotation of dark matter halos could play a key role in shaping these rings, as the gravitational influence of the halo alters the distribution of matter within the galaxy. These galactic rings could, in turn, provide valuable clues about the underlying structure and dynamics of dark matter. As we move further into the study of dark matter halos, it becomes apparent that these structures are far more than just a theoretical construct. They are real, physical phenomena that influence the way galaxies behave. This realization has profound implications for the way we study the universe. For example, scientists have used the concept of dark matter halos to explain the observed rotation curves of galaxies, something that, until recently, had no satisfactory explanation. The rotation curves of galaxies, which describe how the velocity of stars changes with distance from the center of the galaxy, were found to be flat, rather than decreasing as would be expected if only visible matter were present. This observation led to the proposal of dark matter halos as the missing ingredient in the galaxy's mass distribution. The rotation of dark matter halos has since been confirmed through numerous observations and simulations. It is now widely accepted that dark matter halos are responsible for the flat rotation curves observed in galaxies. However, this discovery also led to further questions. For example, why do dark matter halos have such a uniform distribution of mass, and how do they remain stable over such vast periods of time? These questions are still being explored, and the answers could reveal even more about the properties of dark matter. Furthermore, the interaction between rotating dark matter halos and the visible matter in galaxies is not just an academic issue, it has practical consequences for our understanding of galaxy formation and evolution. For example, the behavior of dark matter halos can influence the way galaxies interact with their environment. Galaxies that are part of clusters, for instance, may experience tidal interactions with other galaxies that can distort their dark matter halos. These interactions can lead to the stripping of gas from galaxies, affecting their ability to form new stars. In extreme cases, galaxy collisions can result in the merging of dark matter halos, leading to the formation of larger, more massive halos. These interactions between galaxies and their dark matter halos can also shed light on the dynamics of galaxy clusters. Galaxy clusters are some of the largest structures in the universe, and understanding the role of dark matter in their formation is crucial for understanding the evolution of the universe as a whole. The distribution of dark matter in clusters can help explain the gravitational lensing effect, where light from distant galaxies is bent as it passes through the massive cluster. This effect is one of the primary ways scientists have been able to map the distribution of dark matter in clusters. The study of dark matter halos has also led to the development of more advanced computer simulations that attempt to model the complex interactions between dark matter and visible matter in galaxies. These simulations, which take into account the influence of dark matter halos on the motion of stars and gas, are helping scientists refine their models of galaxy formation. They also allow researchers to test various theories of dark matter, such as whether dark matter is composed of WIMPs, axions, or sterile neutrinos. By comparing the results of these simulations with real observational data, scientists can make more accurate predictions about the behavior of galaxies and their dark matter halos. One of the most exciting prospects for the future of dark matter research is the possibility of direct detection of dark matter particles. While dark matter has been indirectly observed through its gravitational effects, scientists have yet to directly detect dark matter particles. Numerous experiments are underway to detect these particles, including the use of ultra-sensitive detectors placed deep underground to shield them from cosmic radiation. The hope is that by detecting rare interactions between dark matter particles and ordinary matter, scientists will be able to gain a deeper understanding of the nature of dark matter and its role in the universe. As we continue to push the boundaries of our understanding, the study of rotating dark matter halos offers a glimpse into the very heart of cosmic evolution. These halos, while invisible to the naked eye, are key players in the shaping of galaxies and the structure of the universe. The insights gained from studying these halos will not only help us understand the past and present of the cosmos but could also provide the foundation for the next generation of discoveries in astrophysics and cosmology. In the coming years, new telescopes, more powerful simulations, and innovative experiments may provide the breakthroughs needed to solve the mystery of dark matter once and for all. Whether we are looking at galaxy formation, cosmic structure, or the fundamental nature of matter itself, dark matter halos will continue to be a focal point for researchers striving to uncover the hidden truths of our universe. As we venture further into the topic of dark matter and the profound role that rotating dark matter halos play in the universe, the implications continue to unfold in increasingly complex and exciting ways. To fully grasp their importance, we must dive deeper into the physics that governs the dynamics of these halos and consider their possible connection to broader cosmological theories. One of the most intriguing aspects of dark matter halos is their ability to affect the formation and evolution of galaxies in ways that challenge our traditional understanding of gravitational forces. The standard model of cosmology, known as the lambda-CDM model, proposes that dark matter is cold, meaning it moves slowly compared to the speed of light. This assumption forms the backbone of current simulations that attempt to recreate the evolution of large-scale structures in the universe. According to this model, dark matter halos should form in the early universe and gradually grow over time, influencing the structure of galaxies and their interactions with other galaxies and cosmic objects. However, as we examine the specific characteristics of these halos, we begin to realize that the nature of dark matter itself may be more elusive than we previously thought. The interplay between dark matter, visible matter, and dark energy, the mysterious force responsible for the accelerated expansion of the universe, raises fundamental questions about the fabric of reality itself. In recent years, scientists have proposed several alternatives to the cold dark matter (CDM) model, including the possibility of warm dark matter (WDM), or even self-interacting dark matter (SIDM). These alternatives seek to explain some of the phenomena that are difficult to reconcile with traditional models, such as the observed distribution of dark matter in galaxies and galaxy clusters. Warm dark matter, for example, suggests that dark matter particles might be moving faster than previously thought, altering the formation of cosmic structures. This would have significant implications for the structure of dark matter halos, particularly in smaller galaxies and galaxy clusters. If dark matter particles were not cold, their ability to clump together in the early universe might have been significantly reduced, leading to a different pattern of galaxy formation. This alternative theory could offer a better explanation for the smoothness of the cosmic microwave background radiation, the faint glow left over from the Big Bang, which has provided a wealth of information about the early universe. Self-interacting dark matter, on the other hand, offers a fascinating hypothesis that dark matter particles could interact with one another in a way that produces observable effects on the dynamics of galaxies and their halos. In this scenario, dark matter particles could scatter off each other, leading to a redistribution of mass within dark matter halos. This could help to explain the discrepancies between theoretical simulations and observational data regarding the density of dark matter in certain regions of the universe. For instance, it might help resolve the so-called core cusp problem, a long-standing issue in the study of dark matter halos where simulations predict a high-density central cusp of dark matter in galaxies, while observations indicate a flatter distribution. Despite these challenges, the study of rotating dark matter halos continues to provide valuable insights into the workings of the universe. As telescopes improve and our ability to simulate complex cosmic processes increases, it is likely that we will gain a more complete understanding of how these halos evolve over time and how they influence the formation of galaxies. The key to unlocking these mysteries lies in understanding how dark matter interacts with both visible matter and itself, as well as how these interactions are influenced by the expansion of the universe. One of the most exciting recent developments in this field has been the discovery of the phenomenon known as galactic cannibalism. This occurs when one galaxy merges with another, and the gravitational pull of the larger galaxy strips away the stars, gas, and dark matter from the smaller galaxy. This process can dramatically alter the shape and structure of the dark matter halo surrounding the larger galaxy, causing it to expand or contract depending on the specifics of the merger. As more and more galaxies collide and merge, the dark matter halos of these galaxies undergo significant transformations, which in turn affect the dynamics of the entire galactic cluster. Through the study of galactic mergers and the evolution of dark matter halos, scientists are beginning to piece together a more detailed picture of how galaxies grow and evolve over cosmic time. This process has far-reaching implications for our understanding of the universe, as it sheds light on the mechanisms that drive the formation of large-scale structures. For instance, the interactions between dark matter halos and galaxies play a critical role in determining the distribution of stars and gas within galaxies, which directly affects the process of star formation. By studying the behavior of dark matter in these scenarios, scientists can better understand the conditions that foster the birth of new stars and the growth of supermassive black holes. While much of the research on dark matter halos has focused on the larger-scale structures in the universe, recent advances in observational technology have allowed scientists to examine smaller, more localized phenomena. For example, in some dwarf galaxies, dark matter halos appear to be far more diffuse than previously thought. This observation challenges the conventional wisdom that dark matter halos are dense, spherical structures. Instead, it suggests that there may be a range of different dark matter halo profiles, with some being more spread out and others being more concentrated. This discovery has prompted new simulations and theories aimed at explaining the diversity of dark matter halos and how they influence the formation of galaxies across different environments. One particularly fascinating aspect of dark matter halos is their role in the formation of galactic substructures. These are small, satellite galaxies that orbit larger galaxies, often in the outskirts of their dark matter halos. These substructures are thought to be remnants of past interactions or mergers, and their study can provide important clues about the history of galaxy formation. By analyzing the distribution of dark matter in these substructures, scientists hope to gain a better understanding of how dark matter interacts with visible matter in different regions of the universe. The discovery of dark matter substructures has also led to a reevaluation of our understanding of galaxy clusters. These clusters, which contain hundreds or even thousands of galaxies bound together by gravity, are thought to be the largest structures in the universe. The dark matter halos surrounding these clusters are believed to be much more massive than those surrounding individual galaxies, and their rotation plays a crucial role in maintaining the stability of the cluster. By studying the rotation of dark matter halos in galaxy clusters, scientists can gain valuable insights into the dynamics of large-scale cosmic structures and the nature of dark matter itself. In addition to the ongoing theoretical and observational work, the study of rotating dark matter halos has also spurred the development of new experimental techniques. One of the most promising approaches involves the detection of gravitational waves, which are ripples in spacetime caused by the acceleration of massive objects. By detecting the subtle distortions in spacetime caused by the rotation of dark matter halos, scientists hope to gain a direct measure of the properties of dark matter. This approach, though still in its early stages, holds great potential for unlocking some of the deepest mysteries of the universe. Furthermore, the study of dark matter halos is closely tied to the broader search for the elusive particle or particles that make up dark matter. As scientists continue to experiment with various particle detectors and large-scale particle accelerators, they are getting closer to understanding the fundamental nature of dark matter. Whether dark matter consists of weakly interacting massive particles, WIMPs, axions, or some other exotic particle, the search for dark matter is one of the most exciting areas of modern physics. Ultimately, the study of rotating dark matter halos is not just a journey to understand the elusive substance that makes up much of the universe. It is a quest to understand the very structure and dynamics of the cosmos itself. As our tools and techniques continue to evolve, it is likely that we will make even more groundbreaking discoveries about dark matter and its role in the formation of galaxies and cosmic structures. With each new revelation, we move closer to answering some of the most fundamental questions about the nature of reality. As we continue to explore the deeper mysteries of rotating dark matter halos, it's important to appreciate the sheer complexity and significance these halos have in shaping the universe. These structures, despite being composed of an invisible substance, have a profound impact on everything from galaxy formation to the behavior of cosmic clusters. The intriguing part is that while the effects of dark matter are observable, its exact nature remains one of the greatest puzzles in modern astrophysics. The presence of dark matter halos isn't just a theoretical concept, it's backed by a mountain of observational data. One of the key pieces of evidence for dark matter halos comes from the way galaxies rotate. When astronomers observe the rotation curves of galaxies, they notice something unusual. According to Newtonian mechanics, the outer stars of a galaxy should be moving slower than those closer to the galactic center because the visible mass of the galaxy isn't enough to hold the stars at the outer edges. But what astronomers find is that stars in the outer regions of galaxies are moving much faster than expected, suggesting the presence of unseen mass, mass that is gravitationally affecting the galaxy but not visible in any form of electromagnetic radiation. This unseen mass is attributed to dark matter, which doesn't emit, absorb, or reflect light in any detectable way. Instead, its presence is inferred from its gravitational influence on visible matter. But dark matter doesn't just hang around in a galaxy. It forms a massive, invisible halo around it, affecting the galaxy's rotation, structure, and interactions with neighboring galaxies. These halos are far more massive than the galaxies themselves, and they dominate the gravitational field of the system. One of the most remarkable aspects of dark matter halos is their stability. While the visible matter in galaxies, such as stars and gas, is constantly interacting and evolving, the dark matter component remains relatively unaffected by these processes. The dark matter halo essentially remains untouched, even as galaxies undergo violent interactions such as mergers or collisions. This stability gives dark matter a critical role in the long-term evolution of galaxies. Without these halos, galaxies would have a much harder time maintaining their structure, particularly in the face of external gravitational forces from other galaxies or cosmic events. The idea that dark matter halos are essential in maintaining the stability of galaxies is supported by simulations of galaxy formation. In these models, dark matter plays a pivotal role in dictating how galaxies form, evolve, and interact with each other. These simulations suggest that the vast majority of dark matter halos are spherical, with a slight tendency to be flattened near the edges. However, recent observations have shown that not all dark matter halos are perfectly spherical or symmetrical. Some appear to have irregular shapes, likely influenced by nearby galaxy mergers or interactions. This observation adds a layer of complexity to our understanding of how dark matter behaves on the galactic scale. In addition to their influence on galaxy formation, dark matter halos have a profound impact on the dynamics of galaxy clusters. These clusters are the largest gravitationally bound structures in the universe, containing hundreds or thousands of galaxies. The dark matter halos in these clusters are not only much larger than the halos of individual galaxies, but they also play a critical role in determining the overall mass distribution within the cluster. The presence of dark matter in galaxy clusters helps to hold the galaxies together, preventing them from flying apart due to their mutual motion. Dark matter halos in galaxy clusters are also responsible for the phenomenon known as gravitational lensing. This occurs when the gravitational field of a massive object, like a dark matter halo, bends and distorts the light from objects behind it. Gravitational lensing provides astronomers with a unique way to map the distribution of dark matter in galaxy clusters. By studying how light is distorted as it passes through these massive halos, scientists can trace the shape and size of the dark matter halos that are otherwise invisible. This technique has revealed that dark matter is much more widely distributed in galaxy clusters than previously thought, stretching far beyond the visible galaxies themselves. While the role of dark matter halos in galaxy clusters is well established, the question of how they interact with one another is still an area of active research. One of the most exciting areas of study is the concept of dark matter collisions. In certain galaxy clusters, such as the Bullet cluster, two large clusters have collided, and scientists have used gravitational lensing to map the distribution of dark matter before and after the collision. The results suggest that dark matter interacts very weakly with other dark matter, allowing it to pass through the collision without being significantly affected. This behavior provides important clues about the nature of dark matter and its lack of interaction with normal matter. Understanding how dark matter interacts in these extreme environments could help scientists to refine their models of dark matter and its role in the universe. Another intriguing possibility is the potential for dark matter halos to harbor undiscovered types of cosmic structures, such as dark galaxies. These hypothetical galaxies would be composed mostly of dark matter, with very little visible matter. While no dark galaxies have been directly observed, their existence has been proposed to explain certain anomalies in the distribution of dark matter. For example, in some regions of space, there appear to be excesses of dark matter without corresponding visible galaxies. These dark galaxies could potentially account for these excesses, providing another piece to the dark matter puzzle. As we continue to explore the nature of dark matter halos, it's important to consider how these structures fit into our broader understanding of cosmology. Dark matter halos are not isolated phenomena. They are part of a much larger cosmic web. The universe is filled with vast, interconnected networks of galaxies and dark matter that form a giant web-like structure. This cosmic web is a result of the expansion of the universe, with dark matter playing a crucial role in the formation of galaxy clusters, superclusters, and voids. By studying the rotation and structure of dark matter halos within this web, scientists can gain insights into the overall geometry and evolution of the universe. The cosmic web is a vast, intricate structure that shapes the universe on the largest scales. At the center of many of these webs lie supermassive black holes, which are thought to be the engines driving the evolution of galaxies and their dark matter halos. The interactions between dark matter, visible matter, and black holes are central to understanding the future evolution of galaxies and the ultimate fate of the universe. Will dark matter continue to shape the cosmic web as the universe expands? Or will new discoveries about dark matter change our understanding of the universe's fate? As we continue to probe the mysteries of dark matter halos, new observational techniques are allowing us to gather more detailed data than ever before. The advent of next-generation telescopes and space observatories will enable astronomers to study dark matter halos with unprecedented precision. These instruments will provide more accurate measurements of the rotation curves of galaxies, the distribution of dark matter in galaxy clusters, and the dynamics of dark matter in different cosmic environments. This data will help refine our models of galaxy formation, dark matter interactions, and the evolution of large-scale cosmic structures. At the same time, theoretical advancements in the study of dark matter and its properties continue to push the boundaries of our understanding. New simulations that incorporate the latest data are offering more refined predictions about the behavior of dark matter halos. These simulations are helping scientists to explore different dark matter models, including warm dark matter, self-interacting dark matter, and even exotic theories like modified gravity. Each of these models offers a different perspective on the nature of dark matter and its role in shaping the universe, and ongoing research will continue to shed light on which of these models most accurately describes the true nature of dark matter. Ultimately, the study of rotating dark matter halos is not just about understanding a cosmic oddity. It is about exploring the very foundation of the universe. Dark matter halos are key to understanding how galaxies form, how they interact, and how they evolve over cosmic timescales. They offer a window into the invisible forces that govern the cosmos, allowing us to peer into the hidden mechanisms that drive the behavior of galaxies, stars, and even the very fabric of spacetime itself. One of the most remarkable aspects of dark matter halos is their stability. While the visible matter in galaxies, such as stars and gas, is constantly interacting and evolving, the dark matter component of the halo remains relatively stable over cosmological timescales. This stability acts as a gravitational scaffold, holding galaxies together and preventing them from flying apart due to their high rotational speeds. But when we add the element of rotation into these halos, when we speak of rotating dark matter halos, we introduce a new layer of complexity, one that could radically shift how we model the evolution of galaxies. Rotation implies angular momentum, and the idea that dark matter halos might rotate challenges the early assumptions that dark matter, due to its collisionless and non-interactive nature, except via gravity, would lack organized motion. However, recent simulations and observational inferences suggest otherwise. Dark matter halos might indeed possess coherent spin, possibly inherited from the initial conditions of the early universe or through the cumulative torque exerted by cosmic flows and tidal forces over billions of years. This introduces a critical question: what happens when a galaxy is embedded in a rotating dark matter halo? The rotation of the halo could align or misalign with the galactic disk, influencing the angular momentum distribution and even the shape of the galaxy itself. The consequences of such alignment, or lack thereof, are profound. A misaligned rotating halo could create warps in the galactic disk, affect the stability of spiral arms, or even influence the orbits of stars within the galaxy. This would help explain observed features like galactic warping and lopsidedness that have puzzled astronomers for decades. Moreover, rotating dark matter halos could play a key role in the accretion of matter onto galaxies. Galaxies grow by accreting gas, stars, and even smaller galaxies from their surroundings. If the halo itself is spinning, it could help channel infalling material along preferred directions, possibly setting up the spin axis of the galaxy and determining its future morphology. In this context, the angular momentum of the halo becomes a major driver of galaxy formation dynamics. Even more intriguing is how rotating halos might influence dark matter's role in cosmic evolution on the largest scales. Entire galaxy clusters are embedded in massive, overlapping halos of dark matter, and if these structures have net rotation, the effects could be enormous. It could help explain certain anisotropies in cosmic structure, provide insights into the cosmic web's filamentary nature, and influence the motion and merging dynamics of galaxy clusters. Some cosmologists have also speculated that rotating dark matter halos could be connected to an intrinsic property of dark matter particles themselves. If dark matter isn't entirely collisionless but instead possesses some level of interaction, or even an internal structure, then it could naturally develop organized motion under the right conditions. This would suggest a rich dark sector with properties far more complex than a mere cold, inert substance. Rotating dark matter halos could play a key role in the accretion of matter onto galaxies. The angular momentum of the halo might guide the flow of gas and dark matter as they spiral inward, forming stars and structures in specific patterns. This could help explain why some galaxies have thin, well-ordered disks while others are more chaotic or elliptical in shape. If the halo's rotation is aligned with the inflow of gas, it can reinforce the galactic disk spin. But if it's misaligned, it might produce turbulence, leading to more irregular or spheroidal shapes. Furthermore, simulations have shown that rotating halos may also impact the timing and scale of star formation. A rotating halo can act like a cosmic flywheel, regulating the inflow of baryonic matter into the galaxy's center. When the rotation is high, it could delay the collapse of gas clouds, thereby postponing the formation of stars. Conversely, slower rotating halos may allow more rapid star formation early in a galaxy's life. This means that two galaxies with similar masses but different halo spin profiles might have dramatically different star formation histories. The influence of rotating halos doesn't stop at individual galaxies. On a larger scale, dark matter halos interact with one another through gravitational tidal forces, especially during galactic mergers or near passes. If both galaxies have spinning halos, the outcome of their interaction becomes even more complex. The orientation and direction of each halo's rotation can determine whether the merger leads to the formation of a new spiral galaxy, an elliptical galaxy, or even a disrupted tidal structure. This also ties into the phenomenon known as cosmic spin alignment. Some observations and simulations suggest that neighboring galaxies may have spins that are not randomly oriented but exhibit some level of alignment over large scales. If this is true, it implies a deeper coherence in the structure of the universe, possibly rooted in the initial conditions of the Big Bang or influenced by large-scale cosmic filaments. These filaments, the vast bridges of dark matter and gas that connect galaxy clusters, could be transferring angular momentum to the halos as they form and evolve. In fact, cosmic filaments are believed to be fundamental in feeding dark matter and baryonic matter into galaxies. Rotating dark matter halos may act like gravitational turbines, drawing material along these filaments and funneling it into the galaxy in an organized manner. This process would not only contribute to galaxy growth but also shape its rotation and morphology over time. Such a mechanism supports the idea that the spin of a galaxy is not an isolated phenomenon but part of a broader cosmic dance orchestrated by dark matter dynamics. Another compelling aspect of rotating halos involves their potential to explain certain anomalies in galactic rotation curves. While dark matter accounts for the general shape of these curves, there are still subtleties and deviations that standard non-rotating halo models struggle to reproduce. The introduction of halo spin adds a degree of freedom to the models, potentially allowing for better alignment with real observations. For example, a rotating halo could produce asymmetric rotation curves or explain the extended flat regions observed in the outskirts of galaxies. Rotating dark matter halos may also provide insights into the missing satellites problem. According to standard models, many more dwarf galaxies should exist around large galaxies like the Milky Way than are actually observed. One hypothesis is that the rotation of the main galaxy's dark matter halo could be influencing the orbits and survivability of these smaller companions. A fast-rotating halo might disrupt or consume satellite galaxies more efficiently, reducing their long-term visibility. We must also consider the implications for galactic feedback processes. Active galactic nuclei (AGN), which are powered by supermassive black holes at the centers of galaxies, expel massive amounts of energy and material into their surroundings. If the host galaxy's halo is rotating, it could steer the direction of these outflows. This redirection would affect where feedback energy is deposited, which in turn could regulate star formation and gas cooling in different regions of the halo. In clusters of galaxies, rotating dark matter halos could alter how mass and energy are distributed within the intra-cluster medium. For example, if many of the individual galaxies within a cluster have rotating halos, their combined angular momentum could affect the shape and orientation of the cluster's overall dark matter distribution. This might help explain why some galaxy clusters are more elongated or exhibit asymmetric temperature profiles in X-ray observations. Another fascinating possibility is that rotating halos might contribute to the generation of weak magnetic fields in intergalactic space. While dark matter itself is not thought to interact electromagnetically, its gravitational influence on ionized gas could create turbulent flows and rotational shears. These motions might amplify weak seed magnetic fields through a dynamo-like process, eventually contributing to the magnetic structure of galaxies and cosmic voids alike. The connection between halo rotation and gravitational lensing is also worth investigating. Gravitational lensing occurs when massive objects like galaxies or galaxy clusters bend the path of light from background sources. Most lensing models assume spherical or ellipsoidal halos, but if the halos are rotating, the distribution of mass might be more complex than previously thought. This could affect lensing predictions, especially for strong lensing events, and might help resolve discrepancies in lensing data. Rotating halos also raise interesting possibilities in the search for dark matter particle candidates. Different theoretical models predict different behaviors depending on the particle's properties. If dark matter is made of axions, sterile neutrinos, or some exotic WIMP, weakly interacting massive particle, the way it responds to angular momentum and structure formation could vary dramatically. Observing the effects of halo rotation might give us indirect clues about the fundamental nature of dark matter itself. From a philosophical standpoint, the notion of rotating halos forces us to rethink our assumptions about the symmetry and order of the universe. We often model large-scale structures as being static or symmetric for the sake of simplicity, but nature rarely adheres to such simplicity. The presence of spin, even in the invisible scaffolding of the cosmos, suggests that rotation is a universal property, found from subatomic particles to massive galactic structures. This unifying concept could point toward deeper physical laws that have yet to be fully uncovered. And as technology advances, our ability to detect, simulate, and analyze these rotations will improve. Next-generation telescopes, such as the James Webb Space Telescope, the Vera Rubin Observatory, and the Nancy Grace Roman Space Telescope, will provide unprecedented detail in both observation and analysis. Paired with massive computational simulations using supercomputers and AI, we are entering a golden age of cosmology, one where the secrets of rotating dark matter halos may finally be unlocked. This also ties into the phenomenon known as cosmic spin alignment. Studies and simulations suggest that the spin of dark matter halos, and therefore the spin of the galaxies they host, is not entirely random. Instead, there is a statistical tendency for halos in the same large-scale filament of the cosmic web to have aligned spins. This indicates that the universe's structure itself, the vast web of filaments, nodes, and voids, imprints angular momentum onto the dark matter halos during their formation. These alignments suggest that the rotation of a dark matter halo might be influenced as early as the inflationary epoch of the universe. What this means is that rotating dark matter halos are not isolated curiosities. They are deeply embedded within the broader framework of cosmic evolution. Their angular momentum may have originated in the primordial density fluctuations that were stretched and twisted during cosmic inflation. Over billions of years, gravitational torques from surrounding matter structures would have amplified or redirected these rotational properties. This process helps explain why some galactic halos rotate faster or in different directions than others of similar size. Interestingly, the shape of the dark matter halo itself may be influenced by its rotation. Rather than being perfectly spherical, rotating halos are predicted to be oblate, or even triaxial, meaning they are flattened or stretched in certain directions. This anisotropy has implications for the gravitational potential within the halo, which can influence the motion of stars, gas, and satellite galaxies orbiting within or around the host galaxy. It may also affect the way light bends around galaxies, which ties into gravitational lensing studies used to detect and map dark matter distributions. In fact, gravitational lensing offers one of the most powerful observational tools for studying dark matter halos. When light from a distant galaxy passes through a massive foreground object like a galaxy cluster, it bends due to the cluster's gravitational field. The resulting distortion in the background galaxy's image is known as gravitational lensing. By analyzing these distortions, astronomers can reconstruct the shape and mass of the dark matter halo causing the lensing. If the halo is rotating, the mass distribution might be asymmetric in a way that subtly affects the lensing pattern, an effect that advanced telescopes like the James Webb Space Telescope or the Vera C. Rubin Observatory could potentially detect. Another promising method for probing rotating dark matter halos is the analysis of stellar streams. These are long, thin trails of stars that have been gravitationally stripped from satellite galaxies as they orbit a larger host. The path of these stellar streams is influenced by the shape and dynamics of the host galaxy's dark matter halo. If the halo is rotating, it could twist or distort the streams in predictable ways. Careful mapping of these distortions can reveal information about the rotation rate and axis of the halo. On the simulation front, high-resolution cosmological models such as those from the Illustris or Eagle projects have become essential in advancing our understanding of rotating dark matter halos. These simulations include billions of particles representing dark matter, gas, and stars, all interacting under the influence of gravity and other fundamental forces. By tracking how halos form, spin, and merge in these simulated universes, astrophysicists can compare the results with real-world observations. What they've found is that rotating halos can naturally emerge under the right initial conditions, and their rotational properties are closely linked to the environment in which they form. The implications of rotating halos also extend into the realm of dark matter particle physics. If halos are rotating, it may offer indirect evidence about the nature of dark matter particles themselves. For instance, certain hypothetical particles, like sterile neutrinos or self-interacting dark matter, could exhibit different behavior under rotational stress compared to traditional cold dark matter models. The distribution of spin across halos of different sizes might help rule out or support these models. One particularly fascinating idea is that the rotation of dark matter halos could influence the behavior of supermassive black holes at the centers of galaxies. These black holes are known to spin rapidly, and their growth is influenced by the inflow of gas and stars. If the surrounding dark matter halo is rotating, it might channel matter toward the galactic center more efficiently, feeding the black hole and triggering periods of intense quasar activity. This could help explain the observed correlation between black hole mass and galactic bulge mass, which remains a mysterious aspect of galaxy evolution. Moreover, rotating halos might help solve the long-standing problem of disk stability in spiral galaxies. In standard cold dark matter models, galactic disks should be more unstable than they appear. The stabilizing effect of a co-rotating dark matter halo could help suppress spar formation and other instabilities, keeping spiral structures intact over billions of years. This would be a significant revision to current models of disk galaxy evolution, many of which rely heavily on assumptions about the non-rotating nature of halos. In addition, the idea of rotating halos challenges our understanding of galaxy mergers. When two galaxies collide, their halos also interact. If both halos are rotating, especially in different directions, the dynamics of the merger become much more complicated. The rotational inertia of the halos could influence the trajectory of the galaxies, the timing of starburst events, and the structure of the resulting merger remnant. This may help explain why some galactic mergers produce smooth elliptical galaxies, while others leave behind chaotic, irregular systems. This complexity further affects how we interpret the observable universe. For example, when astronomers use redshift surveys to map large-scale structure, they assume a certain distribution of mass based on non-rotating dark matter halos. If many of these halos are actually rotating, it could subtly distort our measurements of galaxy velocities, distances, and clustering. Accounting for this rotational component may refine our models of cosmic expansion and improve estimates of fundamental parameters like the Hubble constant or dark energy density. On the theoretical side, the presence of rotating halos raises deeper questions about the initial conditions of the universe. Why do some halos acquire more angular momentum than others? Are there fundamental symmetries or violations at play during inflation that seed these rotations? Could dark matter rotation be a signature of physics beyond the standard model, perhaps tied to hidden fields or topological defects from the early universe? These are profound questions, still open to exploration. The study of rotating dark matter halos opens up a rich, multidimensional frontier in astrophysics. It challenges traditional assumptions, offers new explanations for observed phenomena, and provides a potential bridge between cosmology, galaxy evolution, and particle physics. The more we investigate this phenomenon, the clearer it becomes that rotation is not just a minor detail, it may be a central, organizing principle of cosmic structure. Rotating dark matter halos have far-reaching implications beyond their theoretical existence. They could offer insights into the behavior of satellite galaxies around larger galaxies, such as the Milky Way. These satellite galaxies often orbit in ways that suggest the influence of the dark matter halo, with many of their orbits being affected by the mass distribution of the halo. When a halo is rotating, it can create asymmetries in the gravitational potential, which in turn affect how the satellite galaxies move. These distortions can potentially be seen in the trajectories of smaller galaxies that are gravitationally bound to a larger galaxy. For example, consider the way galaxies like the Large Magellanic Cloud or the Small Magellanic Cloud interact with the Milky Way. Their orbits are not completely random. They are influenced by the gravitational pull of the Milky Way's dark matter halo. If that halo is rotating, it may cause slight precession in the orbits of these satellites, changing the angle at which they approach the Milky Way. Over millions of years, these interactions might alter the satellite galaxy's orbit in subtle but measurable ways. This is a key area of research, as understanding the effects of halo rotation could provide new insights into the dynamics of galaxy formation and evolution. Another profound consequence of rotating dark matter halos is their potential role in galactic mergers. The universe is littered with galaxy collisions, from minor interactions to full-on mergers. The dynamics of these mergers are not fully understood, but a rotating dark matter halo could play a major role. If two galaxies with rotating halos collide, the interaction between the two halos could be more complicated than traditional models suggest. The rotational momentum of the halos might influence the trajectory of the galaxies themselves, altering the overall dynamics of the merger. This could impact how galaxies form after the collision, whether they result in a smooth elliptical galaxy, or an irregular one, or even an entirely new structure entirely. It might also affect the rate at which supermassive black holes at the centers of these galaxies grow and evolve. In addition, this rotation could have implications for star formation. We know that the presence of dark matter can regulate the formation of galaxies, helping them to accumulate gas, compress it, and trigger star formation. A rotating dark matter halo might affect the rate and distribution of this gas. The rotating halo could induce tidal forces on the gas, causing it to accumulate more efficiently in certain regions, potentially boosting star formation in specific areas of the galaxy. This mechanism could also influence the way that supernovae and other violent cosmic events are distributed within the galaxy, leading to a greater understanding of the temporal evolution of galaxies. Furthermore, the rotation of dark matter halos could have a profound effect on the gravitational stability of galaxies, particularly spiral galaxies. In standard models, galaxy disks are somewhat fragile, subject to instabilities that could cause them to break apart. But a rotating dark matter halo might provide a stabilizing effect, preventing the galaxy's disk from becoming too disturbed. The spin of the dark matter halo could act as a counterbalance to forces like dynamical friction, which typically destabilizes the inner parts of a galaxy. This stability might help explain why some spiral galaxies have remained intact for billions of years, while others have fragmented or evolved into irregular forms. The interplay between dark matter and galaxy morphology is still a topic of intense research. In addition to spiral galaxies, rotating dark matter halos could also explain why some elliptical galaxies appear to have different properties. The rotation of the halo could affect the stellar population and gas dynamics within the galaxy, influencing its shape and color. If dark matter halos are responsible for the formation and maintenance of these galaxies, then understanding their rotation could provide a new method for classifying galaxy types based on their halo characteristics. As we move forward in our understanding of these halos, it's clear that dark matter is far more than just an invisible substance. It shapes the very structure of the universe, and its rotation is an intrinsic part of that process. The study of dark matter halo rotation connects several areas of research in modern cosmology, from galaxy dynamics to high-energy particle physics. As new observational tools and computational models come online, we will likely uncover even more about how dark matter halos spin and what that means for the evolution of galaxies and the larger cosmos. Moreover, simulations of galaxy formation, like those from the Eagle or Illustris projects, are becoming increasingly sophisticated. These simulations model the cosmic evolution of dark matter and galaxies, including the behavior of rotating halos. By comparing the outcomes of these simulations to real-world observations, scientists can refine their understanding of how rotation affects galactic structures. The ultimate goal is to have a comprehensive model that accurately predicts not only the formation of galaxies but also their long-term evolution. These simulations also take into account the potential role of other cosmic phenomena, such as gas inflows, supernova feedback, and black hole growth, which interact with the dark matter halo to shape the galaxies we observe today. In terms of actual observational evidence, we are at the cusp of breakthroughs that could provide more direct confirmation of rotating dark matter halos. Projects like the Vera-C, Rubin Observatory and the next generation of gravitational wave detectors will allow astronomers to better map dark matter halos in real time. These instruments could detect subtle changes in the motion of satellite galaxies or the bending of light around massive objects, giving us a clearer picture of how dark matter interacts with the visible universe. One of the more exciting avenues for future research lies in the detection of dark matter itself. If rotating halos are influencing the distribution of visible matter, they may also affect the direct detection of dark matter particles. Certain types of dark matter, such as axions or sterile neutrinos, could leave traces in the cosmic microwave background or in the interaction rates detected in particle detectors. A deeper understanding of how dark matter halos spin and how they affect galaxy formation could give us clues about the particle properties of dark matter itself. For example, if dark matter particles are more concentrated in regions with fast rotation, that could provide new ways of testing dark matter theories through direct detection experiments. The rotation of dark matter halos is a concept that may change the way we understand the universe. It is a crucial aspect of galaxy formation and evolution, with consequences for the dynamics of satellite galaxies, the outcome of galaxy mergers, and the growth of supermassive black holes. The study of rotating halos also opens up new questions in both observational and theoretical astrophysics, pushing the boundaries of what we know about dark matter and its role in the cosmos. As our tools and theories continue to improve, the mystery surrounding the rotation of dark matter halos will likely be uncovered, offering deeper insights into the very nature of the universe itself. The importance of studying rotating dark matter halos extends beyond just the evolution of galaxies. It also has significant implications for understanding the very foundation of cosmology. By exploring how these halos interact with other components of the universe, we gain a better grasp of the fundamental forces and the underlying structure of spacetime itself. The behavior of dark matter and its rotation could lead to a deeper understanding of the cosmological constant, a mysterious term in Einstein's equations that is thought to account for the accelerating expansion of the universe. Could rotating dark matter halos somehow be tied to this force, perhaps providing new explanations for the phenomenon? It's a tantalizing question that links dark matter, gravity, and the expansion of the universe in ways we are only beginning to explore. Furthermore, the relationship between dark matter and ordinary matter is still one of the most profound puzzles in modern physics. In the case of rotating dark matter halos, their influence on galaxies and other cosmic structures can provide critical clues about this interaction. For example, as dark matter shapes the structure of galaxies, it also dictates the distribution of ordinary matter, such as stars, gas, and dust. The effect of dark matter rotation on the dynamics of these components is something that scientists are keen to investigate further. Understanding how the rotation of dark matter halos interacts with baryonic matter could allow for breakthroughs in understanding how galaxies are assembled, and why they take the shapes and sizes that they do. The search for clues regarding the presence of rotating dark matter halos is intimately connected to one of the key challenges in modern cosmology: the nature of dark matter itself. Despite being responsible for a significant portion of the mass in the universe, dark matter remains invisible to all traditional forms of detection. It interacts only via gravity and possibly weak nuclear forces, making it incredibly difficult to study directly. However, the effects of dark matter, particularly in how it rotates and shapes galaxies, can be indirectly observed. By focusing on the motion of stars and gas within galaxies and analyzing gravitational lensing effects, scientists hope to detect subtle signatures of dark matter rotation. Any such discovery would bring us closer to understanding not just the nature of dark matter but also how it interacts with the visible universe in complex and previously unknown ways. The influence of rotating dark matter halos could extend to a variety of cosmic phenomena, such as the formation of cosmic voids. These large, empty regions in space are not truly empty. They contain low-density gas and dark matter. The formation and evolution of these voids are intricately linked to the large-scale distribution of dark matter. It's possible that the rotation of dark matter halos contributes to the expansion of these voids, pushing galaxies apart and causing the universe to grow at an accelerated pace. This interaction between rotating halos and voids could provide new insights into the accelerated expansion of the universe, shedding light on the forces that drive cosmic inflation and the nature of dark energy. Simultaneously, the effects of dark matter halo rotation could also influence the behavior of cosmic filaments, which are vast, thread-like structures that connect galaxies across the universe. These filaments are made of dark matter and gas, and they play a crucial role in the formation of galaxies and clusters of galaxies. The gravitational pull of dark matter filaments helps to gather matter and facilitate the formation of galaxies along these paths. If these filaments are influenced by rotating dark matter halos, they could be dynamically altered, causing the matter within them to move in specific ways. This could affect the distribution of galaxies along filaments, and lead to a more nuanced understanding of the large-scale structure of the universe. The study of rotating dark matter halos could also have an important impact on astrophysical simulations. Many current simulations of galaxy formation treat dark matter halos as static, non-rotating structures. However, as we continue to learn more about the actual dynamics of these halos, it's likely that future simulations will need to account for rotation. This would significantly change the way we model galaxy mergers, the dynamics of galactic disks, and even the growth of supermassive black holes. By incorporating rotation into these models, scientists can create more accurate simulations that better reflect the real behavior of galaxies and their surrounding dark matter halos. Incorporating the effects of rotation into these models would also affect the predictions for the growth and evolution of supermassive black holes. These enigmatic objects are found at the centers of most large galaxies, and their formation is thought to be closely tied to the dynamics of the surrounding dark matter halo. The rotation of the dark matter halo could affect how matter flows into the black hole, influencing the rate of accretion and the growth of the black hole. This, in turn, could provide new insights into how supermassive black holes influence their host galaxies and contribute to the regulation of star formation. Understanding the relationship between dark matter halo rotation and black hole growth could also help explain the role that these black holes play in the larger scale structure of the universe. The potential to connect the rotation of dark matter halos with observations of galaxy formation, cosmic voids, and supermassive black holes opens up new research avenues. Over the next few decades, as observational techniques improve and computational models become more advanced, the study of rotating dark matter halos is likely to become a central focus in the field of astrophysics. This research could lead to groundbreaking discoveries about the true nature of dark matter and its role in shaping the universe. It could also pave the way for new theories that explain how galaxies evolve over time and how dark matter itself interacts with the fabric of spacetime. For now, the rotation of dark matter halos remains a fascinating and complex topic at the frontier of scientific research. With advancements in technology, both observational and computational, we are closer than ever to unlocking the secrets of these mysterious cosmic structures. As we continue to probe deeper into the nature of dark matter, the impact of its rotation on the universe will undoubtedly become clearer. The questions surrounding rotating dark matter halos challenge our understanding of the cosmos, and may ultimately reshape our entire view of the universe's evolution. As our understanding of dark matter progresses, one of the most exciting aspects of studying rotating dark matter halos is the possibility that it could offer new insights into the behavior of the universe on the largest scales. The idea that dark matter might not just be an invisible, passive component of the cosmos, but instead a dynamic force capable of influencing the shape and rotation of galaxies, is a revolutionary concept. It suggests that the universe is far more interconnected than we previously realized, with dark matter playing a much more active role in the ongoing processes of cosmic evolution. With rotating dark matter halos, the possibility of a more unified theory of cosmic dynamics is within reach. The discovery that dark matter may exhibit rotational behavior changes our view of galaxy formation as well. Until recently, it was assumed that dark matter halos were spherical in nature, more or less static and evenly distributed around galaxies. However, the hypothesis that these halos may rotate introduces the notion of dynamism, suggesting that they are actively participating in the gravitational shaping of galaxies. This is a stark departure from older models, which treated dark matter halos as simple, non-rotating, and static entities. Now, as astronomers and physicists dive deeper into observational data, they may find that these rotating halos could be responsible for some of the unexpected behaviors observed in galaxies, such as their shape and the distribution of stars within them. One intriguing possibility that arises from this is the impact of dark matter rotation on the overall stability of galaxies. If dark matter halos rotate in a particular way, they could exert a stabilizing influence on the galaxy's structure. In this scenario, the rotation of dark matter halos might not only be influencing the rotation of galaxies themselves, but could also be playing a role in preventing galaxies from disintegrating under the gravitational forces that act on them. This dynamic interplay between dark matter, ordinary matter, and gravity could hold the key to understanding why some galaxies remain stable and others don't, helping to refine our models of galaxy evolution. Moreover, the connection between rotating dark matter halos and galaxy stability could extend beyond the simple motion of stars and gas. It may provide answers to one of the key open questions in cosmology: why do galaxies not fly apart due to the forces acting on them? According to our current understanding of gravity, without the influence of dark matter, the visible matter in galaxies would not have enough mass to stay together. Yet, when we observe galaxies, they remain intact despite the fact that the visible matter seems insufficient to account for their observed motions. This is where dark matter comes into play, and the rotation of dark matter halos may provide additional insights into this stability by influencing the overall distribution of mass in a galaxy. In terms of gravitational effects, the rotational behavior of dark matter halos could also impact how we perceive the curvature of spacetime around galaxies. Einstein's theory of general relativity tells us that mass and energy warp spacetime, and in turn, this curvature dictates how objects move through space. If rotating dark matter halos add a new layer of mass distribution within galaxies, this could change how we perceive the curvature of space around them. Future experiments and observations could reveal subtle gravitational effects around galaxies that we've never noticed before. It's possible that these effects are a direct result of the interaction between rotating dark matter halos and the visible matter in galaxies, as well as their gravitational pull. The implications of rotating dark matter halos don't stop at individual galaxies. As astronomers examine the structure of the universe on even larger scales, the role of dark matter and its rotational influence becomes even more significant. The large-scale structure of the universe, which includes vast networks of galaxy clusters, superclusters, and cosmic voids, may be heavily influenced by the dynamics of dark matter. The way in which dark matter interacts with the distribution of galaxies could provide a new explanation for the arrangement of these structures across the cosmos. In particular, the role of rotating dark matter halos in the formation of galaxy clusters could help us better understand how these massive cosmic structures evolve over time. One interesting area of research is the relationship between dark matter rotation and the cosmic web, the intricate structure of interconnected galaxy clusters and voids that spans the universe. As galaxies and dark matter are thought to be connected through cosmic filaments, the rotation of dark matter halos may play a critical role in the way these filaments form and evolve. If dark matter halos rotate in particular ways, this could influence the growth of filaments and their ability to link galaxies together. This, in turn, could provide clues about how large-scale cosmic structures formed in the early universe and how they continue to evolve today. Researchers may also find that dark matter's rotational effects contribute to the observed motions of galaxies within these filaments, further expanding our understanding of the cosmic web. The evolution of the cosmic web and the way that dark matter halos rotate could also provide insights into the origins of the universe itself. The study of rotating dark matter halos and their connection to large-scale structure formation may offer clues to the mechanisms behind the early universe's expansion. Did dark matter play a central role in driving the initial expansion of the cosmos? If rotating dark matter halos influenced the formation of galaxies and their distribution in the universe, could they also have been a driving force behind the initial conditions of the Big Bang? These questions are not only foundational to cosmology but could also help scientists construct a more comprehensive model of the universe's birth and early evolution. The search for evidence of rotating dark matter halos is only beginning, but the potential discoveries are nothing short of revolutionary. If future research validates the idea of rotating halos, it could lead to a paradigm shift in our understanding of dark matter. Rather than seeing dark matter as a static entity that merely influences the motion of galaxies from the sidelines, it could be revealed as a dynamic and active participant in the universe's most fundamental processes. The discovery of rotation within dark matter halos could spark a new era of cosmological theory, one where dark matter is recognized as a more complex and multifaceted force than we ever imagined. This research is also crucial for testing and refining the standard model of cosmology, known as the lambda cold dark matter model. While this model has been incredibly successful in explaining the large-scale structure of the universe, there are still gaps and unanswered questions. The introduction of rotating dark matter halos into our models could provide a more nuanced explanation for some of these unresolved issues. For example, it might help explain the precise formation of galaxy clusters or the nature of cosmic voids. By examining the effects of rotation on dark matter halos, we may uncover new physics that challenges or enhances our current understanding of the universe's evolution. The prospect of uncovering the true nature of dark matter, especially through the study of rotating dark matter halos, brings us closer to answering some of the most profound questions about the universe. How did the universe form? What is the true nature of dark matter? How does dark matter influence the larger-scale structure of the cosmos? These questions are fundamental to our understanding of the universe, and the exploration of rotating dark matter halos may very well provide the answers we seek. As scientists continue to push the boundaries of our knowledge, the exploration of rotating dark matter halos also invites us to rethink the tools and methods we use to observe the universe. Traditional methods of studying galaxies, such as optical telescopes that rely on visible light, are limited in their ability to detect the elusive dark matter. Instead, scientists are turning to more advanced techniques, such as gravitational lensing and radio waves, to observe the effects of dark matter and its rotation. Gravitational lensing, for example, takes advantage of the fact that light from distant objects is bent and distorted by the massive gravitational pull of dark matter. By studying the distortions in the light, scientists can map out the distribution of dark matter in a galaxy, including its potential rotation. Another promising method is the study of galaxy rotation curves. For years, astronomers have observed that the stars at the edges of galaxies move faster than they should, given the visible matter present. This discrepancy led to the hypothesis that there is unseen mass, dark matter, surrounding galaxies. By studying the rotation curves in more detail and applying the concept of rotating dark matter halos, scientists can refine their models of how galaxies behave and how dark matter contributes to their rotational dynamics. As our observational technology improves, so too will our ability to detect and understand the subtle rotational effects of dark matter. One of the most intriguing aspects of this research is the possibility that rotating dark matter halos could reveal a deeper connection between the universe's visible and invisible components. The distribution and behavior of dark matter may not just influence galaxy structure but could also offer clues about the fundamental laws of physics that govern the universe. For example, the interactions between dark matter and ordinary matter might offer a glimpse into physics beyond the standard model. This could help scientists answer questions that have puzzled them for decades, such as whether dark matter interacts with other forces in ways we haven't yet detected or if there are other, unknown forms of matter that we have yet to discover. The study of rotating dark matter halos could also provide important implications for our understanding of cosmological simulations. Modern cosmological models, which aim to simulate the evolution of the universe from the Big Bang to the present, rely on the properties of dark matter to predict how galaxies and structures form. If dark matter halos are rotating, it could change the dynamics of these simulations, requiring physicists to update their models. For instance, simulations could more accurately depict the motions of stars and galaxies by incorporating the rotational aspects of dark matter, leading to more realistic depictions of how galaxies grow, evolve, and interact with each other. Furthermore, the discovery of rotating dark matter halos could help answer broader questions about the very nature of gravity. The presence of rotating halos might offer insight into the fundamental nature of gravitational forces, potentially leading to new discoveries in gravitational physics. Could rotating dark matter halos point to new gravitational interactions or even offer a hint toward the long-sought theory of quantum gravity? These are questions that could be answered through careful study and analysis of dark matter's role in the rotational behavior of galaxies. This opens the door to a new chapter in our understanding of both gravity and dark matter, potentially revolutionizing our perception of the universe's foundational laws. Even beyond the confines of galaxies, rotating dark matter halos may play a role in the behavior of the universe on the largest scales. For instance, dark matter is believed to be responsible for the formation of the cosmic web, a vast network of galaxies and galaxy clusters that stretches across the universe. If dark matter halos rotate, this could affect the way in which galaxies and clusters are arranged within the cosmic web, potentially influencing the structure and evolution of the universe itself. The influence of rotating dark matter halos may extend beyond individual galaxies, playing a crucial role in the growth and development of large-scale cosmic structures. As scientists continue to investigate the properties of rotating dark matter halos, they are likely to encounter unexpected findings that challenge existing models. It's possible that dark matter's rotational dynamics could reveal entirely new forces or phenomena that have eluded us so far. For example, could rotating dark matter halos have a role in the acceleration of the universe's expansion? The discovery of such a connection would have profound implications for our understanding of dark energy, the mysterious force that drives the accelerated expansion of the universe. If dark matter's rotation influences the expansion rate of the universe in any way, this could open the door to a new understanding of the universe's ultimate fate. The ongoing research into rotating dark matter halos may also shed light on other cosmic mysteries, such as the nature of galactic mergers. When two galaxies collide and merge, they undergo complex gravitational interactions that can reshape their structure. The role of dark matter in these events is still a subject of much debate. If dark matter halos rotate, they could play a significant role in the way galaxies merge and interact with each other. The rotational behavior of dark matter may help explain the observed dynamics of galactic mergers and provide a more comprehensive model for understanding these events. In addition to these large-scale cosmic phenomena, the study of rotating dark matter halos may also have practical implications for our understanding of fundamental physics. As we learn more about how dark matter behaves, it could inform our search for dark matter particles in laboratory experiments. The detection of dark matter particles has been one of the most elusive goals in modern physics, with experiments attempting to capture interactions between dark matter and ordinary matter. If rotating dark matter halos provide new insights into dark matter's properties, it could help refine the techniques and methods used in these experiments, bringing us closer to a direct detection of dark matter. Furthermore, the search for rotating dark matter halos may inspire new technologies and innovations. As astronomers develop more advanced observational techniques to study dark matter, they are likely to encounter new challenges that will require innovative solutions. The development of specialized telescopes, detectors, and computational tools to observe and simulate dark matter could have far-reaching applications beyond cosmology. These advances could lead to new technologies in fields such as materials science, computing, and even energy production. In the broader context of science and discovery, the investigation of rotating dark matter halos represents a crucial step toward unlocking the secrets of the universe. Dark matter is one of the most enigmatic and mysterious components of the cosmos, and understanding its behavior is essential to gaining a more complete picture of the universe's past, present, and future. By exploring the rotational dynamics of dark matter halos, scientists are laying the groundwork for future breakthroughs in cosmology, particle physics, and our understanding of the fundamental forces of nature. The study of rotating dark matter halos has the potential to be a transformative area of research, one that could change the way we think about galaxies, dark matter, gravity, and even the origins of the universe itself. It challenges our conventional understanding of how the universe works, offering the tantalizing possibility that dark matter is more than just a passive player in the cosmos. It could be an active force that shapes the very fabric of the universe. With each new discovery, we move closer to unraveling one of the most profound mysteries in science, one that has the potential to reshape our understanding of the universe on the grandest scale. As the exploration of rotating dark matter halos continues, we find ourselves standing at the edge of new frontiers in both theoretical and observational astrophysics. The implications of this research are far-reaching, extending not only to our understanding of dark matter itself but also to the broader cosmic framework that governs all celestial phenomena. One of the most fascinating aspects of dark matter's rotational behavior is how it might help explain the formation and behavior of galaxies in greater detail. The traditional understanding of galaxy formation has largely focused on the idea that matter clumps together under gravity, eventually leading to the creation of stars, planets, and other observable structures. However, with dark matter playing such a significant role in the creation of these structures, understanding how it rotates could hold the key to understanding how galaxies, as well as galaxy clusters, are shaped and maintained over billions of years. Dark matter halos that rotate may create a more complex gravitational environment around galaxies than we previously imagined. Rather than being a uniform, static presence around a galaxy, the rotation of these halos could contribute to the unique spiral shapes of galaxies or the elliptical forms seen in galaxy clusters. The rotation of dark matter may influence how stars and gas clouds within a galaxy move, further impacting the dynamics of the galaxy. The way in which dark matter interacts with visible matter could lead to more accurate models of galactic evolution and the forces that shape them, offering an explanation for phenomena that have remained puzzling in the past. One of the challenges facing researchers in this field is the inherent difficulty of detecting and measuring dark matter's rotation directly. Unlike visible matter, which emits electromagnetic radiation that can be observed using telescopes, dark matter does not interact with light in the same way. This means that we are left to observe its effects on the surrounding matter, such as through gravitational lensing, galaxy rotation curves, and simulations. While these methods have already provided us with substantial clues about dark matter's role in the cosmos, they still represent indirect evidence. With the development of more sophisticated tools and techniques, however, there is hope that we will eventually be able to observe the effects of rotating dark matter halos in greater detail, potentially leading to more direct observations in the future. As we delve deeper into the mechanics of rotating dark matter halos, one of the fundamental questions that arise is whether the properties of these halos could be consistent across different galaxies or whether each galaxy's dark matter halo behaves uniquely. There is some evidence to suggest that dark matter halos might have a common structure, with their rotation curves following similar patterns across galaxies of all sizes. This would imply that dark matter behaves in a similar way regardless of the galaxy's environment, suggesting that dark matter is a universal component of the cosmos. However, there is also evidence that the properties of dark matter halos could vary depending on the size, age, and structure of the galaxy. Some galaxies may have halos that rotate more rapidly or more slowly than others, which could be influenced by factors such as the galaxy's environment or the presence of nearby galaxy clusters. This variability in the behavior of dark matter halos across different galaxies raises intriguing questions about the underlying nature of dark matter and the forces that govern its interactions with visible matter. The continued study of rotating dark matter halos will also likely lead to new insights into the formation of galaxy clusters. These vast structures, which consist of hundreds or even thousands of galaxies bound together by gravity, are some of the most massive objects in the universe. Dark matter plays a critical role in the formation and evolution of galaxy clusters, acting as the invisible scaffolding that holds the galaxies together. If dark matter halos are indeed rotating, this could alter the way in which galaxies within a cluster interact with one another. The rotation of dark matter may influence the overall shape and distribution of galaxies within the cluster, potentially leading to new insights into the dynamics of galaxy cluster formation and evolution. Another fascinating avenue of research is the potential relationship between rotating dark matter halos and other mysterious cosmic phenomena, such as the formation of supermassive black holes. Supermassive black holes are found at the centers of most galaxies, and their formation is still not fully understood. It is believed that these massive objects play a crucial role in the growth and evolution of galaxies, influencing the movement of stars and gas around them. Dark matter halos, particularly those that rotate, may interact with the material surrounding a supermassive black hole in ways that could impact its growth and behavior. Understanding the connection between rotating dark matter halos and black holes could help shed light on the role of these enigmatic objects in the cosmos. The interplay between dark matter and visible matter is another key area of investigation. The presence of dark matter halos around galaxies could have a profound effect on the movement of stars, gas, and dust within the galaxy. If dark matter halos are rotating, this could introduce additional forces that influence the dynamics of these visible components. For example, the rotational motion of dark matter may cause the stars in a galaxy to move in ways that differ from the predictions made by models that do not account for the rotation of dark matter. This could lead to new insights into the kinematics of galaxies, helping to refine our understanding of how stars move and interact within their cosmic environment. It's also possible that the study of rotating dark matter halos will contribute to the search for dark matter particles in laboratory experiments. The connection between dark matter's rotational dynamics and its fundamental properties could provide clues that lead to a better understanding of the particle nature of dark matter. This could have significant implications for ongoing efforts to detect dark matter through direct and indirect means. Experiments such as those conducted at the Large Hadron Collider, LHC, and underground detectors designed to capture dark matter particles may one day yield evidence that supports the theoretical predictions about the properties of dark matter. As exciting as these prospects are, they also bring to light a number of challenges. The mystery of dark matter is, at its core, a problem of detection. Despite years of theoretical modeling and indirect evidence, no one has yet been able to detect dark matter directly. The study of rotating dark matter halos is one of the most promising areas of research, but it also requires innovative observational techniques and advancements in technology. Instruments that can detect subtle gravitational effects, as well as simulations that can account for complex interactions between dark matter and visible matter, will be key to unlocking the mysteries of these enigmatic halos. In the near future, advancements in both observational astronomy and theoretical physics may allow scientists to address these challenges head-on. As more data is gathered, and as our understanding of the universe's fundamental forces continues to evolve, we may find ourselves in a position to solve some of the deepest questions about dark matter and its role in the universe. The discovery of rotating dark matter halos is just one piece of the puzzle, but it may very well be a pivotal piece, guiding future research and opening up new avenues of investigation into the nature of the cosmos itself. The ongoing pursuit of understanding rotating dark matter halos may also shed light on the broader structure of the universe itself. As scientists work to observe and model the behavior of dark matter, they are simultaneously unraveling the intricate connections between galaxies, clusters of galaxies, and the mysterious dark energy that seems to be driving the accelerated expansion of the universe. The study of dark matter halos provides a critical piece in this grand puzzle, as it allows us to probe the invisible scaffolding that holds everything together. As we learn more about how dark matter behaves, both individually and in relation to visible matter, we gain deeper insights into the fundamental laws of the universe that govern everything from the smallest particles to the largest cosmic structures. One potential breakthrough on the horizon comes from the intersection of quantum mechanics and general relativity. Dark matter, with its apparent lack of interaction with light, challenges many aspects of our traditional understanding of the universe. As dark matter is thought to be governed by gravitational forces, it offers a unique opportunity to explore the relationship between quantum effects and gravitational effects, two areas of physics that are famously difficult to reconcile. In particular, the study of rotating dark matter halos may open new doors for theorists seeking to merge these two realms, offering fresh perspectives on quantum gravity, the nature of spacetime, and the very fabric of the universe. These discoveries could ultimately lead to new theories that extend far beyond our current models of physics. Another intriguing area of research involves the impact that rotating dark matter halos could have on the formation of large-scale cosmic structures. Over the course of cosmic history, matter has clumped together to form galaxies, clusters of galaxies, and even superclusters. The rotation of dark matter halos around these structures could be a critical factor in shaping their evolution. For example, dark matter may play a significant role in preventing galaxies from being torn apart by internal forces. The gravitational pull of dark matter could act as a stabilizing force, helping to preserve the integrity of these systems over billions of years. Without the presence of dark matter and its rotational dynamics, galaxies and clusters might not have been able to form or evolve as we see them today. This idea adds another layer of complexity to our understanding of how galaxies come into being and how they continue to evolve throughout cosmic history. Moreover, the study of rotating dark matter halos is pushing the boundaries of our observational capabilities. Traditional telescopes and detectors are limited in what they can measure, primarily relying on the light emitted by visible matter. Dark matter, however, is not directly observable in the same way. To study the rotation of these halos, scientists must rely on indirect methods such as gravitational lensing, where the mass of dark matter distorts light passing through it, allowing researchers to infer its presence and properties. The use of gravitational lensing has already proven to be a valuable tool in the study of dark matter, but as technology advances, so too will our ability to measure the subtle effects of dark matter's rotation. The next generation of telescopes and observatories will likely provide a wealth of new data that could revolutionize our understanding of rotating dark matter halos. Instruments such as the James Webb Space Telescope, JWST, and other upcoming space missions are poised to explore the farthest reaches of the universe, providing unprecedented insights into the nature of dark matter. By examining distant galaxies and galaxy clusters, these new instruments will be able to collect data on the gravitational effects of dark matter halos, potentially allowing scientists to detect and measure their rotation with greater precision than ever before. This data could lead to a deeper understanding of how dark matter influences the formation and evolution of galaxies across cosmic time. Beyond this, the study of rotating dark matter halos could have profound implications for our understanding of the future of the universe. As dark matter interacts with visible matter and influences the motion of galaxies and other cosmic objects, its behavior may hold the key to understanding the ultimate fate of the universe itself. If dark matter plays a significant role in the expansion and dynamics of the cosmos, understanding how it behaves could provide important clues about the long-term trajectory of the universe. For example, the continued study of rotating dark matter halos may help answer questions about the eventual slowing or acceleration of cosmic expansion. Could the interaction of dark matter with dark energy lead to a change in the rate of expansion over time? Is there a link between dark matter's rotation and the possible fates of the universe, such as a big crunch, or a scenario in which the universe continues expanding indefinitely? As we continue to study rotating dark matter halos, we may find that they are connected to other cosmic phenomena in ways we have yet to fully comprehend. The structure of these halos may be intricately linked to the formation of cosmic voids, the vast, empty regions of space that exist between galaxies and galaxy clusters. These voids are thought to be the result of the gravitational influence of dark matter, which draws galaxies and clusters toward one another while leaving large expanses of empty space between them. The rotational behavior of dark matter halos could play a significant role in shaping these voids, offering insights into their origins and evolution. The relationship between rotating dark matter halos and cosmic voids could reveal new patterns in the large-scale structure of the universe, deepening our understanding of how galaxies and clusters are distributed across space. In addition to its impact on large-scale structures, rotating dark matter halos could also have implications for smaller-scale phenomena. The movement of dark matter within a galaxy's halo could affect the motion of individual stars and planetary systems. For instance, the gravitational pull of rotating dark matter might influence the orbits of stars, causing them to move in ways that would not be predicted by models that ignore dark matter's presence. These interactions could also have implications for the formation and evolution of planetary systems, potentially altering the conditions under which planets form and evolve over time. Understanding these effects could provide a more comprehensive picture of how galaxies and their constituent stars and planets develop and behave. The connection between rotating dark matter halos and the search for dark matter particles remains an exciting frontier in astrophysics. Despite the challenges of detecting dark matter directly, scientists are increasingly optimistic that new methods will emerge that allow us to observe its effects with greater precision. Researchers are investigating a wide range of potential dark matter candidates, from weakly interacting massive particles, WIMPs, to axions and sterile neutrinos. These particles, if they exist, could be responsible for the dark matter that makes up a significant portion of the universe's mass. By studying the rotational dynamics of dark matter halos, scientists may be able to gain crucial information about the properties of these particles, providing a clearer path toward their detection. The study of rotating dark matter halos also holds the potential to spark new theoretical breakthroughs in the field of cosmology. As scientists continue to refine their models of dark matter, they may uncover new insights into the fundamental nature of the universe itself. The connection between dark matter, dark energy, and the large-scale structure of the cosmos could lead to the development of entirely new theories that challenge our current understanding of space, time, and gravity. With each new discovery, we move closer to answering some of the most profound questions in science, including the nature of dark matter, the fate of the universe, and the fundamental forces that shape the cosmos. As the exploration of rotating dark matter halos continues, it is clear that we are standing at the edge of a new era in cosmological research. With each breakthrough, we are revealing a more complex and interwoven picture of the universe. As scientists gather more data and improve their understanding of dark matter, it becomes increasingly likely that we will be able to tie together many of the loose ends in our current models of cosmic evolution. These discoveries may not only advance our comprehension of the universe's origins and its ongoing development, but also transform our understanding of fundamental physics itself. One of the most exciting aspects of studying rotating dark matter halos is that they can offer insights into the most extreme conditions of the universe. Dark matter halos, particularly those that surround the largest galaxies and galaxy clusters, often exhibit behaviors that cannot be replicated under laboratory conditions. These phenomena occur under the influence of unimaginable gravitational forces, temperatures, and other environmental factors. By observing and studying these extreme conditions, we may be able to learn more about the fundamental laws of physics and how they govern the universe at large scales. This knowledge may ultimately have applications that extend far beyond astrophysics, perhaps informing the development of new technologies or providing insights into problems that remain unsolved in other areas of science. Additionally, rotating dark matter halos could have implications for our understanding of the fundamental forces that shape the universe. Traditionally, we have understood the universe through the lens of four fundamental forces: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. However, the study of dark matter and its rotational dynamics may point to new forces or interactions that were previously unknown. These forces could act on scales far larger than anything we have previously studied, possibly revealing new principles of physics that exist on the boundary between the observable and the unobservable. It's possible that dark matter's interaction with visible matter, through the mechanism of rotation in halos, could unlock new aspects of gravitational theory or even lead to the discovery of entirely new forces, revolutionizing our understanding of the universe at its most basic level. This journey of discovery might also reveal more about the elusive nature of dark energy, the mysterious force that is driving the accelerated expansion of the universe. Dark matter and dark energy are often considered two sides of the same coin, both comprising a significant portion of the universe's mass-energy budget, yet they have distinct properties and effects. While dark matter exerts gravitational influence and tends to clump together to form structures like halos, dark energy seems to work in the opposite way, pushing objects apart and driving the expansion of the universe. Understanding how rotating dark matter halos behave could potentially shed light on the interaction between these two cosmic forces and provide clues about how the universe's expansion will unfold over time. Could the behavior of dark matter and halos provide us with insights into the future of cosmic acceleration? These questions continue to provoke intense debate among cosmologists and physicists. Moreover, as astronomers continue to explore the universe, new techniques are being developed that could dramatically improve our ability to detect and study dark matter. In particular, advancements in gravitational wave astronomy are beginning to provide new opportunities for studying cosmic phenomena at unprecedented levels of detail. Gravitational waves, ripples in space-time caused by the acceleration of massive objects, could provide a new avenue for detecting the subtle effects of dark matter and rotating halos. As these waves travel across the universe, they carry with them a wealth of information about the objects that created them. By analyzing these waves, scientists might be able to uncover further details about the dynamics of dark matter, including its rotational behavior. The integration of gravitational wave data with other astronomical observations could open up an entirely new frontier in our understanding of dark matter and its role in the cosmos. In addition to technological advancements, the growing international collaboration between researchers is accelerating the pace of discovery. Astronomical and astrophysical research is no longer limited to a single country or institution. The global network of telescopes, space observatories, and laboratories working together has significantly expanded our observational reach. This collaborative effort has led to the rapid accumulation of data on dark matter halos, allowing scientists to compare findings from different regions of the universe. By pooling their resources, these scientists can cross-check results, develop more accurate models, and refine their understanding of dark matter. This global cooperation is helping to turn what once seemed like an impossible challenge into one of the most exciting and achievable scientific endeavors of our time. The future of dark matter research also hinges on the development of more refined simulation techniques. These simulations, which use advanced computational power to model the behavior of dark matter in galaxies and other large-scale cosmic structures, have been crucial in our current understanding of dark matter halos. However, as our models grow more sophisticated and our data more abundant, the complexity of these simulations also increases. Researchers are constantly working to refine their computational methods, ensuring that their simulations reflect reality as accurately as possible. These improvements are helping to bridge the gap between theory and observation, allowing us to test and verify the predictions made by our models in ways that were not possible just a few years ago. By improving simulation accuracy, scientists are not only increasing our knowledge of dark matter but are also improving our broader understanding of how galaxies and other cosmic structures evolve over time. One of the most fundamental challenges in the study of rotating dark matter halos is the fact that dark matter remains invisible to conventional observational techniques. Its presence can only be inferred through its gravitational effects on visible matter, such as stars and galaxies. This limitation has led to the development of more creative observational methods, including the use of gravitational lensing. When light from a distant galaxy passes through a dark matter halo, the gravity of the halo bends and distorts the light, creating a lensing effect. By studying these lensing patterns, astronomers can map the distribution of dark matter within halos, allowing them to infer both its density and its rotation. While this technique has provided valuable insights, it still leaves many questions unanswered. For instance, the exact nature of the rotation of dark matter within halos is still poorly understood. However, as technology improves and more sophisticated instruments are developed, we can expect these techniques to become even more precise, leading to deeper insights into the behavior of dark matter. As we continue to refine our understanding of rotating dark matter halos, one question that remains at the forefront of astrophysical research is how dark matter interacts with visible matter. While we know that dark matter interacts gravitationally with normal matter, it is still unclear whether it has any other types of interaction, such as electromagnetic or weak force interactions. Most current models of dark matter assume that it does not interact significantly with ordinary matter except through gravity. However, this assumption is based on indirect evidence, and some theories suggest that dark matter may have other, more subtle interactions that we have yet to detect. If these interactions exist, they could radically change our understanding of the behavior of dark matter halos and their role in the evolution of galaxies. Another key question is whether dark matter is truly made up of one particle species or whether it consists of multiple, yet unidentified, components. If dark matter is composed of several types of particles, the rotation of dark matter halos could vary depending on the relative abundance of each particle type. For instance, different particles might cluster together in different ways, resulting in halos with varying rotational patterns. Understanding these variations could provide crucial insights into the fundamental nature of dark matter and its role in cosmic structure formation. The hunt for dark matter candidates, such as WIMPs, axions, and sterile neutrinos, continues to be a major focus of research, with each new discovery bringing us one step closer to solving the dark matter mystery. As we continue to probe deeper into the intricate behavior of rotating dark matter halos, we begin to uncover more about the cosmic environment in which they exist. The relationship between dark matter halos and the galaxies they surround is far more complex than previously thought. Dark matter halos are not merely passive structures that form around galaxies and clusters of galaxies. They are active participants in the formation, evolution, and even the destruction of cosmic structures. Their gravitational influence shapes the galaxies they encircle, guiding the distribution of stars, gas, and other visible matter within them. The rotation of dark matter halos is thought to play a pivotal role in the dynamics of these galaxies, influencing everything from star formation rates to the interaction between galaxies and dense cosmic environments. This interaction between dark matter halos and visible matter has led to a number of intriguing observations. For instance, galaxies that reside within larger galaxy clusters often exhibit peculiar rotation curves, which are typically characterized by a flat or slowly declining velocity profile as a function of distance from the center of the galaxy. This is in stark contrast to the expected behavior of visible matter, which should experience a decreasing velocity the farther it is from the galaxy's center due to the declining gravitational influence of the visible mass. However, the rotation curves of galaxies indicate that there is an unseen mass, likely dark matter, extending far beyond the visible region, providing the gravitational support necessary to explain these anomalous velocities. Moreover, recent studies have suggested that the shape and behavior of rotating dark matter halos could offer insight into the broader evolution of galaxies. In particular, the size, density, and rotational speed of these halos might correlate with key factors such as a galaxy's morphological type, its star formation history, and even the distribution of its gas. Galaxies with more massive dark matter halos tend to be more stable, with a smoother distribution of stars and gas, while galaxies with less massive halos are often more prone to tidal interactions and have less organized structures. This relationship has spurred new investigations into the role of dark matter in galaxy mergers, as the interaction between dark matter halos during these events can influence the outcome of the merger, potentially leading to the formation of elliptical galaxies or the triggering of intense star formation. However, as much as we have learned about rotating dark matter halos, there is still much that remains enigmatic. For example, scientists are still grappling with the question of how these halos form and evolve over cosmic time. Are they primordial structures, forming in the early universe in the wake of the Big Bang, or are they the result of later processes such as mergers between smaller halos or the accretion of dark matter from the cosmic web? Understanding the origins and evolution of dark matter halos is crucial to understanding the larger cosmic landscape, as these halos provide the scaffolding around which galaxies, clusters, and even larger cosmic structures are built. Another puzzle lies in the potential for dark matter to have different properties depending on its location within a galaxy or cluster. While dark matter is often modeled as a single, homogeneous substance, some recent theories suggest that its properties may vary depending on its environment. For example, dark matter in the outskirts of a galaxy may exhibit different rotational characteristics than dark matter closer to the center, possibly due to the influence of surrounding gas, stars, and magnetic fields. This could have significant implications for the way dark matter halos are modeled, requiring a more nuanced approach that accounts for regional variations in dark matter density and behavior. In addition to these observational challenges, there are also ongoing theoretical debates regarding the nature of dark matter itself. The leading candidate for dark matter is the so-called weakly interacting massive particle, WIMP, which is predicted to interact only via the weak nuclear force and gravity. While WIMPs remain the most popular theoretical model for dark matter, recent developments in experimental physics have begun to call their existence into question. No direct evidence for WIMPs has been observed, and some researchers have proposed alternative candidates for dark matter, such as axions, sterile neutrinos, or even modifications to our understanding of gravity itself. These alternative theories could potentially lead to different rotational behaviors in dark matter halos, altering our expectations and predictions for how these halos behave in different environments. One promising area of research involves the study of dark matter clumps, or subhalos, within larger dark matter halos. These smaller structures, which may be the remnants of early dark matter clumping during the universe's formative years, could be responsible for certain irregularities observed in the rotation curves of galaxies. In some cases, the motion of stars within a galaxy appears to be influenced by the gravitational pull of these subhalos, which may explain the presence of wiggles or other unexpected features in galaxy rotation curves. If these subhalos are confirmed to exist, they could provide valuable insights into the distribution and behavior of dark matter on smaller scales and contribute to a more detailed picture of dark matter halos overall. This focus on small-scale structures also opens up new possibilities for studying dark matter halos through gravitational lensing. By examining how light from distant objects is distorted by the gravitational influence of dark matter, astronomers can map out the distribution of dark matter in unprecedented detail. Some recent advances in gravitational lensing technology have allowed for the identification of subhalo candidates, shedding light on the hidden complexities of dark matter halos. As observational techniques continue to improve, we can expect even more precise measurements of these substructures, allowing for a deeper understanding of the role they play in the larger-scale behavior of dark matter halos. Another exciting avenue of research involves the role of dark matter halos in the formation and growth of supermassive black holes. Supermassive black holes, which are thought to exist at the centers of most galaxies, may owe much of their growth to the interactions between the black hole and the surrounding dark matter halo. The gravitational pull of dark matter could funnel material toward the black hole, helping to feed its growth over cosmic time. Additionally, the behavior of dark matter in the vicinity of black holes could provide valuable clues about the relationship between dark matter and the strong gravitational fields near these extreme objects. The study of rotating dark matter halos, therefore, may not only provide insight into the structure of galaxies but also the processes that govern the formation of some of the most enigmatic objects in the universe. While we still have much to learn about rotating dark matter halos, the research that is currently underway offers a tantalizing glimpse into the future of cosmology. As technology advances and our understanding of the universe deepens, we can expect to answer many of the questions that currently elude us. The study of dark matter, and its rotational dynamics in particular, is likely to play a central role in shaping our understanding of the universe's past, present, and future. What began as a theoretical pursuit has evolved into one of the most exciting and promising fields of modern science. With each new discovery, we are uncovering a deeper and more intricate picture of the universe, one that holds the potential to transform our understanding of reality itself. As scientists continue to investigate the properties of rotating dark matter halos, they are not just unraveling the mysteries of dark matter, but also charting a course toward a more comprehensive understanding of the cosmos. The answers to the many questions that remain will likely shape the next great chapter in the story of human knowledge and exploration. Whether we are on the brink of a paradigm shift in our understanding of dark matter, or merely at the beginning of a longer journey, the future of research in this field promises to be filled with exciting discoveries that could redefine everything we know about the universe. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.